All right, good afternoon. Let's go on the record, please. I'm Charlotte Mitchell, Chair of the Utilities Commission, and with me are the following commissioners. When I call your name, please announce your presence. Commissioner Brown Bland,
I'm present.
Commissioner Clodfelter,
Yes, good afternoon.
Commissioner Duffley,
I'm present.
Commissioner Hughes,
Here.
Commissioner McKissick,
Present.
and Commissioner Kimmerite. I now call to order docket number E-2 sub 1300, which is captioned in the matter of Duke Energy Progress LLC's request to initiate technical conference regarding the projected transmission and distribution projects to be included in a performance-based rate-making application. North Carolina General Statute Section 62-133.16 authorizes performance-based regulation, or PBR, for electric public utilities. Pursuant to statutory directive, on February 10th, 2022, the Commission issued an order adopting Commission Rule R1-17B, which implements this statute. On June 8th, 2022, Duke Energy Progress, LLC, or DEP, filed a letter with the Commission indicating its intent to file a notice of intent to file general rate application that includes a performance-based regulation application, as authorized under North Carolina General Statute 62-133.16, with the PBR application targeted for filing no earlier than October 6th, 2022. DEP also requested, pursuant to Rule R117B, that the Commission initiate a technical conference regarding the projected transmission and distribution projects to be included in the PBR application. On June 15th, 2022, the Commission issued its order scheduling technical conference and setting procedures for technical conference, scheduling the technical conference to be held on this date, July 25th, 2022, beginning at 2 o'clock. The purpose of this technical conference, which is required by statute, is to allow DEP to present information regarding its projected transmission and distribution expenditures. The Commission's June 15th order permits interested parties with the opportunity to intervene in the docket and to provide comment on DEP's filing. The order also permits parties an opportunity to make a presentation today, subject to an advance notice requirement. Upon the filing of timely motions, the following parties have petitioned to and have been allowed to intervene in this proceeding: the Carolina Industrial Group for Fair Utility Rates 2, Carolina Utilities Customer Association, North Carolina Justice Center, North Carolina Housing Coalition, and the Southern Alliance for Clean Energy, to which I'll collectively refer to as NCJC, the North Carolina Sustainable Energy Association, Vote Solar, the Natural Resources Defense Council, or the NRDC, and the North Carolina Electric Membership Corporation filed a petition to intervene, which was denied. But NCEMC has been allowed limited participation rights and will be allowed to participate in the technical conference today, if so willing. The North Carolina Attorney General's Office has provided notice of its intervention in this proceeding pursuant to North Carolina General Statute Section 62-20, and the public staff, which represents the using and consuming public in matters before the Commission, has provided notice of its intent to participate in the technical conference today. On July 15th, 2022, DEP filed its projected transmission and distribution expenditures. In accordance with the Commission's order issued on June 15th, parties may file written comments on DEP's filing through today, July 25th. That brings us to today. Today, we're going to hear first from DEP. There'll be no cross-examination of the DEP witnesses per the terms of the statute, but commissioners will be permitted to ask questions of DEP's witnesses. There will be no questions taken on Commission's questions. Parties who've indicated an intent to present will be allowed no more than 10 minutes each to make such presentation. The Commission will hear from those parties in the following order: the public staff, the Attorney General's Office, NCEMC, SIGFR, NCJC, NCSEA, and Vote Solar. This technical conference is being transcribed, and the transcript will be filed in the docket as soon as it's available. Please, as is always the case, do your best today to avoid interference with our court reporter's ability to transcribe the proceeding. All right, before we begin, I'd like to ask the parties to identify themselves for purposes of the record. We'll start with DEP.
Thank you, Chair Mitchell. Members of the Commission, I'm Jim Jeffries with the law firm of McGuire Woods, and I'm here today along with my co-counsel, Ms. Melissa Butler, from the law firm of Troutman Pepper, and we're here on behalf of Duke Energy Progress, LLC. And we've also, since we're presenting first, if I may, I'd go ahead and introduce our presenters.
Let's hang on one second. Let me get counsel first, and then I'll come back to you for that. All right. Good afternoon, Mr. Jeffries and Ms. Butler. All right.
Nadia Lohr with the public staff on behalf of the using and consuming public.
Good afternoon, Ms. Lure.
Good afternoon, Christina Kress with the law firm of Bailey and Dixon here on behalf of Sigbert 2.
Good afternoon, Ms. Kress.
Taylor Jones on behalf of the NCSEA.
Good afternoon, Ms. Jones.
Good afternoon, Chair Mitchell, Commissioners. David Neal on behalf of North Carolina Justice Center, North Carolina Housing Coalition, Southern Alliance for Clean Energy, and Natural Resources Defense Council joined together with
Okay.
Justice Center.
Thank you.
Good afternoon. My name is Margaret Force with the Attorney General's Office, representing the using and consuming public.
Good afternoon, Ms. Force.
Good afternoon, Peter Ledford, also on behalf of NCSEA.
Good afternoon, Mr. Ledford.
And David Drews representing Vote Solar. Jake Duncan is the staff from Vote Solar is here today. He is not going to be making oral comments, and thus I'll probably step out early as he will just be an observer.
All right. Thank you, Mr. Drews.
Good afternoon, Chair Mitchell, member of the commission. I'm Tim Dodge here with North Carolina Electric Membership Corporation. And we do not plan to make any presentations today.
All right. Good afternoon, Mr. Dodge. All right. Thank you, council. Before we begin, any preliminary matters? All right. We will go ahead and get started. Mr. Jeffries, Ms. Butler, y'all may proceed.
Thank you, Chair Mitchell. I'd like to begin by introducing the three presenters for Duke Energy Progress today in the order in which they will present. And from the commission's right to left, we have Mr. Justin Brown, who is the Director of Planning and Regulatory Support for Duke Energy. In the center, we have Mr. Brent Guyton, who is the Director of Asset Management for Customer Delivery for Duke Energy. And on the commission's left, we have Mr. Dan Maley, who is the Director of Transmission Compliance Coordination for Duke Energy. And at this point, we would turn the presentation over to Mr. Brown.
All right. Good afternoon, gentlemen. You may proceed.
Good afternoon. Good afternoon. Thank you to all the attendees who have joined us today for this technical conference. I know your time is valuable. Hopefully you'll find today's material informative. Again, my name is Justin Brown. I'm Director of Planning and Regulatory Support for Duke Energy. I have seated next to me two experts that will be speaking on distribution and transmission investments that will be included in the multi-year rate plan projects. First speaker is Brent Guyton, Director of Distribution Asset Management. Brent will be followed by Dan Maley, Director of Transmission Compliance and Coordination. So we'll spend the next few minutes going through and hearing from the experts on discrete and identifiable distribution and transmission related projects that we expect to file in our multi-year rate plan. Over the course really of this technical conference, we're going to provide an overview of the trends that are impacting our industry and drive our system planning. We're also going to share an overview of the distribution and transmission projects, as I mentioned earlier, that were included in our pre-conference technical documentation filed back on July 15th. These investments are necessary for the company to both maintain and advance the grid to support the clean energy transition in North Carolina. Additionally, our speakers are going to provide specific examples of projects and programs to be included in the multi-year rate period. It's also important to note that the presentation today, we're going to go over at a high level. It's not going to go through every piece of documentation that we previously filed, but hope to give a good overview of those. Just as a reminder, the documents that we did share in advance on July 15th provide really a detailed description of each planned improvement program or project, the purpose and description of those projects, of the work to be completed, a summary of benefits, the estimated installation costs for both T and D work. Additionally, we provide a complete list of the planned projects that included the projected in-service dates, the estimated total costs for each individual project, along with House Bill 951 policy considerations that are addressed. And lastly, cost-benefit analyses. We did list costs and benefits of each program and project, and many included a financially based cost-benefit analysis. Clicker's not working. Oh, there we go. All right. We want to address upfront the federal grants being the Infrastructure Investment Jobs Act, IIJA, We are actively engaged in ongoing implementation of the Federal Infrastructure Investment Jobs Act at the state and federal level. We are participating in requests for information and also having discussions both at the federal level with the Department of Energy, Department of Transportation, as well as the EPA. For instance, we did file a RFI in early June, June 2nd, along with 5 other RFI responses that have been submitted, I believe, in the open docket before the commission already, the IIJA docket. While federal agencies are making progress, they still are in the early phases of the implementation of the federal grants, with many activities under development. While programs are under development, the company is defining and working through a prioritization process that includes building a framework and operating model with a partnership with an outside firm that we plan to benchmark against our industry peers. The process will include proactive grant planning. We expect the grant windows to be fairly short, 60 to 90 days when those become available. So we kind of need to have our act together in that approach. It also includes grant writing, submittal, and our execution plans associated with that. The team is going to carefully review those grants and may apply at both the federal and state level to participate. Our goal is essentially to maximize the impact of those grants for customers in North Carolina. We look forward to the funding opportunities that are expected to become available in the fourth quarter of this year. But to be clear, we are pursuing the funding opportunities for the benefit of customers, and we will ensure that they receive the benefits associated with those grants. The projects included in our multi-year rate plan and in the materials submitted on July 15th, however, don't include an assumption for any grants received. The projects benefit customers regardless of whether the grant opportunities are made available to the company. So none of the cost benefit analysis or the listing of costs and benefits assume any grant awards. So overall, I believe we would all agree that our grid is in a complex transition. The original design of our grid was somewhat simple and had a few key design assumptions that were in place. One, that overall generation was firm and dispatchable, that generation generally followed load and always kept the power in balance. Load at the distribution level of the system was treated more as a passive load, as opposed that was attached to the transmission system. Power flowed generally in one direction from central generation to the customer, and the grid was designed for reliability. Overall, the mission of the electric utility has significantly changed over the decades. Our mission used to be to keep the lights on, keep the lights on, and keep the lights on. Now, today, we are faced with other considerations. One, we have to be cyber secure. We have to be physically secure. The grid has to be flexible and enabling new technologies that are coming on the grid. We have to be accessible, economical, clean, and sustainable. And utmost, we have to be resilient. Today, those original design assumptions that I mentioned earlier are being challenged. We introduced back in 2019 megatrends or trends that we are looking at that are affecting our grid investments. Those are still present today. One being grid improvement technologies. Overall, those technologies are continuing to advance at a very high rate. Spending in smart grid IT and analytics overall is expected to grow to $6 billion by 2028. Technological advancements with renewables and DERs is growing rapidly, especially here in North Carolina. As I mentioned earlier, threats to grid infrastructure, unfortunately, is troublesome. In the U.S., ransomware attacks are up by 148% over 2020. The impact of weather events is increasing in frequency. North Carolina has been impacted 6 times by billion-dollar storms in some way in 2021, and 9 of those billion-dollar storms in 2020, the most in North Carolina history. Concentrated population growth continues to occur in North Carolina. North Carolina has 2 cities, Charlotte and Raleigh, that are among the top 25 cities growing in the United States. Customer expectations are continuing to evolve, with reliability and affordability being key to their feedback topics to us. And finally, environmental commitments, both at the federal, state, and local levels. Fortune 500 companies are seeking places to invest that have carbon reduction and sustainability in mind. 60% of the Fortune 500 companies have carbon goals, much of those located in North Carolina. And key among that is House Bill 951. House Bill 951 established aggressive carbon goals, 70% by 2030 and net zero by 2050. The grid improvements proposed are necessary to not only maintain our grid, but also support the clean energy transition and the overall resiliency of our grid in North Carolina. When we start thinking about the future of the grid, we have to start thinking about it as an enabler. The grid has to be thought of as an enabler for new technologies that safely integrates new grid edge technologies, growing DER technologies such as solar, wind, storage, and electric vehicles. To do this, the legacy grid must be upgraded and adapted to accommodate two-way power flow, load shifting, and greater situational awareness. Traditional forms of grid planning are no longer adequate. The company has implemented Integrated Systems Operation Planning, or ISOP, and those plans leverage more and more data, such as the propensity to adopt solar and the purchase of electric vehicles, and all that has been implemented into our planning processes. Overall, programs will use new processes to implement tailored solutions that essentially is going to build a digital superstructure grid that delivers on the energy goals for North Carolina and the requirements for our state. So when we start thinking about the overall strategy and the future grid, a couple of things bubble up to mind. Three primary objectives really come to mind. One is overall grid resiliency. We must have a grid that has the ability to withstand and recover from frequent extreme weather events and external hazards. The grid must be more resilient if we're going to have more and more DER attached to the distribution system overall. Expansions of renewables and DER, the grid must be able to meet that customer demand and be able to accommodate it. If North Carolina has a bold carbon goal, both the distribution and transmission system must be ready for that challenge. And overall, finally, equitable access to benefits. We must achieve a balanced outcome for all customers across the state to be able to accommodate and be able to leverage the new energy technologies and solutions that are coming. And all of this has to be done with an eye towards the most efficient manner of implementation and affordability. So next, I'm going to turn it over to Brent Guyton that'll dive into the distribution programs. Brent?
Right. Thank you, Justin, and good afternoon, everyone. My name is Brent Guyton. I'm the Director of Asset Management for distribution here in the Carolinas. During my portion of the presentation today, I'm going to cover 6 areas. One, benefits to customers. Also talk about the 4 critical grid capabilities needed to achieve the objectives that Justin just touched on. I'll also overview the work streams and programs that are in our distribution projects. Also, the planning approach that we've leveraged to maximize benefits to our customers. I'll also overview a specific MYRP project in our coastal zone in the greater Wilmington area. And then lastly, I'll highlight the 10 program summaries that make up our MYRP projects and the work streams within those. Before I do that, I want to talk briefly about how we will be delivering the benefits to the customers and establishing and/or strengthening those critical grid capabilities that I'll describe shortly. I'll explain this more as we go along through my part of the presentation, but I want to introduce it here as we get started. So our projects are planned for a set of geographically clustered substations. Each substation, based on its specific needs to achieve those grid capabilities, will receive selected distribution improvement programs. It is not a one-size-fits-all. You will see that as I talk about the specific project for the coastal area. And lastly, the work is executed geographically for those clustered substations to maximize 1, resource efficiency, 2, minimize the disruption to our customers while we're performing the work, and also deliver the customer benefits across a broad customer area or footprint. As we complete that work, all of that infrastructure is uplifted as to the new grid capabilities. So the benefits from doing this work, first off, reliability. Fewer and shorter outages. I'll describe some of the programs that will support this, from self-optimizing grid to targeted underground, as well as others. Resiliency, as Justin talked about, physical and cyber attacks are certainly a threat, but also severe weather impacts. We have specific programs and work to deal with those as well. Access to renewables and distributed energy resources. Capacity and voltage regulation, two of the work streams that we have in our distribution project specifically address the ability for two-way power flow to support DER, as well as the voltage regulation and management needed with fluctuations in voltage from intermittency in rooftop solar. The MYRP projects and the grid capabilities they bring are foundational for future work and support future technologies. Justin talked about the advancements in grid technologies being one of the mega trends. This work is foundational that we can build on going forward. With enhanced automation and control and also situational awareness, we can operate the grid more efficiently. That's in our control centers. The situational awareness that the operators in those grid and the control rooms have allow them to make better real-time decisions, as well as for the automated systems in those control rooms to execute things more effectively and efficiently. Also, with the automation and communication, there are huge amounts of new data that we're generating daily that we can leverage to build additional customer programs and offerings to allow them to have more choice around affordability and control of their energy use. And equitable access to benefits. I talked about that a moment ago. As we complete our MYRP projects, they're across a broad footprint geographic area and uplift those assets and provide the benefits to all the customers in those areas. The strategy that we're implementing as we go through this is foundation and will support customers in the future. The programs and work that we're doing within MYRP projects truly do make the grid more flexible and adaptable, again, to support two-way power flow and distributed energy resources as an example. I talked a moment ago about the automation and control technologies and generating huge amounts of data. Not only is that great for our operators and situational awareness, that's also leveraged by our planning engineers for future planning cycles, leveraging the ISOP tool sets and the subsets of tools underneath integrated system resource planning, operations planning, sorry. And as the grid technologies continue to advance, they'll be integrated into new solutions that will be able to address changing customer needs as well. So I mentioned the critical grid capabilities, and you see the four listed here: reliability, capacity, automation, and communication, as well as voltage regulation. And let me touch on reliability. There's a historical view and understanding of what reliability means and the impact of outages. That changes in the world as we go forward with distributed energy resources. So let me describe that a little bit. So in the past, the distribution grid, as Justin described, was built to serve customers' load. And when there was an outage, customers, residential as well as commercial industrial, certainly residential if they had a home-based business, and then commercial industrial, there was an impact to commerce or loss of revenue in that particular instance. And also, if someone now in today's world is a hybrid employee or a completely virtual employee working from home, that outage is now impacting their ability to do their job. And that's not been the history that we've had. And also, along with that, homeschooling. That has become more the norm, not just from a COVID standpoint, but continuing to grow. That impacts education for our children in the future when we have an outage and interrupts their learning process. So now fast forward to the future, when we have distributed energy resources that are connected to the distribution grid. Now it is no longer just that traditional impact that I just described. We're impacting the ability of generation to connect and supply power to the grid when we have an outage. You layer into that electric vehicle charging. There's now an impact of an outage, whether it be fleet electrification at a business or charging a personal vehicle at home. That outage now has an impact on transportation. That has not been the case in the past from a reliability perspective. So very different lens at which we look at reliability going forward. Capacity next. It is critical for two-way power flow to build appropriate hosting capacity into the grid. And there's a traditional view of capacity to just serve traditional loads, but now we've got to layer in both that electric vehicle charging as well as distributed energy resources. And we do that with our Morecast tools under ISOP to take in and look at that information, and I'll describe that more in a little bit. Automation and communication. The self-optimizing grid program is really a cornerstone program that defines resiliency. We're able to have a fault condition on the distribution grid. The system in less than a minute detects where that problem is and automatically reroutes power around that. The ability to take a punch and recover quickly, at least in my mind, is the definition of resiliency, and that program does that. And lastly, voltage regulation. We have always had voltage regulation on the distribution grid to follow traditional load moving up and down throughout the day or during the hours of the day. But as we introduce more and more distributed energy resources and you have cloud cover passing over, and a generating site can go from maximum generation to minimum generation in seconds or parts of a second, and do that multiple times during the day. We've got to be able to manage that type of fluctuation in voltage on the distribution grid. That requires new capabilities in voltage regulation management. So that's a lot, four broad categories of grid capabilities in my description. What I'd like to share is really kind of an analogy of how I see all this coming together. So I want you to think about the vehicle that maybe you learned to drive on or you rode in with your grandparents as you were growing up, and think about the technology that was in that vehicle versus the one that you probably used to commute to this meeting today, or maybe sitting at home in your garage now. When I think about reliability or longevity, we used to talk about tune-ups for old cars. You don't hear that term anymore. The cycles of maintenance are much more extended, last longer without having to do any maintenance on those vehicles. Efficiency. Likely the vehicles of today, at least for gasoline or diesel engine, they're smaller than the historical vehicles and yet much more powerful and much more efficient based on where they are today. When I think about automation, the first example of automation I can think of in vehicles, it was an automatic transmission versus a manual or a standard shift transmission. We now have things such as climate control automation, Bluetooth connections to your phone, self-parking vehicles is now part of the automation we see in vehicles today. Control or advances in control. Same thing, I think of cruise control as one of the earliest examples I can think of for control in a vehicle. We now have anti-lock brakes as well as radar on a vehicle where if you set your cruise control and you begin to encroach on the vehicle in front of you, it will automatically slow your vehicle down, adjust your speed to maintain a safe following distance. As that vehicle moves out of the way or you change lanes, it will automatically move you back up to your speed while maintaining that distance. And lastly, situational awareness. In the older vehicles, you may have had a rear view mirror or side view mirrors, and now they're surrounded with cameras. Again, radar on the front of the vehicle to look at closing distance on other vehicles. Think about what you have inside the vehicle with the dash. A simple gauge cluster potentially with a speedometer in the past, and now there's a touchscreen driver information center with multiple screens that you can advance to make any changes in the vehicles. That's the type of transition that I see in the advancements in technology that's necessary on the distribution grid, and we're on that pathway now. But that gives a broader view, at least in my mind, of how that moves, and one that hopefully most of us can relate to. So I want to talk about the programs themselves that make up our projects. You'll see on the left-hand side of this graph the projected spend over the 3 rate years, October 23 through the end of September of 26. Total of $1.8 billion projected for the work in the distribution projects. There's 3 categories you see, with substation and line making up the majority of those, but also hazard tree removal, as well as retail and system capacity. You'll see those listed again in the center of the table there. And then also there's details further over to the right. One thing I want to point out and speak to is that within substation and line, you see capacity. It's the very first detail that you see listed there at the top. You'll also see hazard tree removal, one up from the bottom in the substation and line category. But you'll also see retail and system capacity listed separately, and also hazard tree removal. In both cases, that's the same work. It's where it's happening geographically that's the difference for those. The capacity work is not only serving traditional loads, but also additional capacity for electric vehicles and distributed energy resources. Within substation and line, it is geographically located with another critical mass of work that can all be executed together as a large project. Whereas the standalone capacity is identified thermal overloads for the 3-year rate rate periods that we need to be addressed, but they are not physically adjacent to other critical work that we can execute as a larger project. The same thing for hazard tree removal. It's the same work both in the substation and line areas as well as the standalone. As part of our integrated vegetation management plans, we have maintenance of our right-of-ways. So the prescribed right-of-ways around our distribution lines that we maintain and remove vegetation within the right-of-way. Hazard tree removal is focused on threats from outside the right-of-way, dead, diseased, dying, or otherwise structurally unsound trees that can fall into the right-of-way and damage and contact our facilities. So again, both those are needed. We've identified trees that are outside and away from the other projects, as well as some that are geographically located where we can execute at one point. The 10 programs that are part of the substation and line, There are short descriptions here on the page, I think, that are very descriptive. Again, capacity is about line capacity, both traditional DER as well as EV. Self-optimizing grid, or the self-thinking grid, you may have heard that term, is about detecting faults and automatically rerouting power to restore as many customers as possible. Voltage regulation, I described that as one of the critical grid capabilities, and we also are describing a program that directly adds that capability in. Hardening and resiliency, Justin touched on that as one of the key areas for the grid to strengthen and avoid threats. Specifically, there are three areas I'll talk about as we go into the program summaries, and these are focused on more physical threats, both severe weather as well as other impacts to the grid. Distribution automation, adding automated restoration capabilities at certain portions of our lines. Also equipment retrofit. This is focused on three different asset classes: transformers, arrestor stations, and riser poles. And riser poles are where our facilities transition from overhead to underground. That last pole where the conductors transition to underground is referred to as a riser pole. There's some equipment modifications that we can make on those to make those more reliable. Long duration interruption. This is looking at areas of our system where the facilities are hard to access. They typically are more remote customers, geographically isolated, where we may serve entire communities or groups of customers, and we have higher than normal duration outages when they do have an event. And I'll talk more about that as well. Targeted undergrounding is a data-driven approach to look more at the laterals of our system and where we have unusually high frequency of outages, and potentially placing those underground and also relocating from typically rear lot to front lot as well. I talked about hazard tree removal, and I'll describe that more as we get to the program summary. And then lastly, infrastructure integrity. This is about looking at the foundation of the grid on which we'll build all the other work that's there and make sure everything is intact while we're in that area executing those larger projects, make sure everything is where it needs to be to support the ongoing needs of our customers. For that. All right, I want to talk about how we actually plan and build out and assemble the MYRP projects. Overarching this, and I'll go ahead and say this here, the integrated systems and operation planning tool sets are a key part of this, especially for our distribution planning engineers with the advanced distribution planning tool sets, as well as the Morecast load data that's leveraged to look at capacity needs going forward. I'm going to start on the graphic and really from kind of the lower left at that 7 o'clock position and work my way around clockwise as we get through this. So planning engineers, they are assigned a geographic area. There's a set of substations and circuits that they have personal responsibility for to do all the analysis and load flows and calculations that are necessary there. They do that at a circuit level, but they're also looking broader across the area at the roll up to substations and their areas also. The first thing to do is leverage the Morecast data set. That's a 10-year hourly view within our ISOT tool sets, providing load information for the planners to analyze. It not only looks at traditional loads, but also electric vehicle impacts as well as distributed energy resource impacts as well. And all that's included in that capacity analysis. They're also looking at the other critical grid capabilities I mentioned, reliability, voltage regulation, as well as automation and communication. Once they've identified that current state and where there are potential gaps in the capabilities for those individual circuits, those are then looked at across all 10 of those programs to layer in an approach to look at what the benefits are that could be delivered to customers and how we could actually raise the capabilities for those circuits. That then is really the balanced circuit approach, the outcome of that, looking at what's needed for individual circuits. And again, it's not a one size fits all. It's based on the analysis they've done of what the needs are for those individual circuits. This is where you see in the middle of the graphic, you see project development and also asset management listed. The duties I've spoken to so far are within asset management. But this next step is where project development gets involved. So they collect and intake all that information from the planning engineers across the system and start to do a system level analysis. What is all the work that is necessary across the system within this particular MYRP period? That then is iterated against things such as any potential labor constraints, any material issues that we may know about, as well as annual budgets. That is an iterative process, and then these are the annual plans to be developed into MYRP projects. That then begins the process of sequencing that work at high level schedules for the individual substations, and then those geographically clustered stations, that is all aggregated together to form the MYRP projects. for that. One thing I want to mention is I've talked about Morecast being a 10-year hourly forecast to look out over that 10-year horizon. That 10-year horizon is necessary to truly give transmission and generation a view of what impacts distribution will have on the overall system and how they incorporate that into the integrated resource plan. The planning engineers, while they have that 10-year view, they're not looking to scope projects and solve problems that are in years 6 through 10. They are focused on years 3 through 5. What are the near-term thermal issues, automation capabilities, voltage regulation needs, as well as reliability in that 3 to 5 year window? That's the work that needs to be executed now and planned now for the next 3 years. We will then come back and analyze again in the future and continue that iteration and pick up those out year projects as appropriate in the future. So again, a proper planning horizon, not overbuilding, but looking at that near-term needs for the grid. So we'll take a look at a project. This is a fairly busy slide, but before I move over into the table, I want to talk about what's in the box on the left. And I talked about this earlier, so I'm going to circle back to some of my earlier comments. The project-based approach that we leverage. Again, we analyze at the circuit level, roll that up into plans for a geographically set of substation or geographically located substations. We select only the improvement programs that are needed. It's not a one-size-fits-all. What are the things needed for those circuits? And again, only in that 3 to 5 year window. And lastly, the improvement programs are selected. Those are then rolled into MYRP projects to be executed and also at that geographically clustered level. And the reasons for that is to maximize resource efficiency. We move and mobilize into an area, do all the work that's necessary, and then demobilize and move to the next area. That minimizes customer disruptions. Yes, we're still there working, but we're in there and out of there as efficiently as we can. And when we leave, the benefits to the customers are all there. Everything that we were going to do on behalf of the customer is complete as we roll out of that area and move to the next area. I'll share another analogy I think that helps describe this a little better. Think about a house remodel, and I'm not talking about one individual room. I'm talking about a whole house type of remodel. The first thing you'll do is think about what the needs are that you have for your house. There may be things that are end-of-life assets. You may want to improve the efficiency of your home. Maybe it's an older home, replace windows, doors, insulation, new HVAC system. Maybe the plumbing is an older vintage of metal pipes as opposed to modern plastic pipes. There may be things that you need from a home automation standpoint, upgrades to appliances, et cetera, possibly a new roof. You may have to start taking care of aging parents. You may have to create an aging in place benefits in areas in your home to be able to accommodate them. So once you've identified all that, there's a couple of ways you could execute that house remodel. One, you could do a lot of small individual projects. It likely takes a long time. Future projects, as you do the smaller ones, may end up impacting a project you just finished, and it may cause you to undo something you just did to complete the next little project. It certainly seems less efficient, and the disruption to you and your family as you're going through this remodel seems to go on forever. There's no end in sight for what's going on there. And even as you complete each of the individual projects, it's really hard to appreciate the benefit that you've brought by completing that one project because there's so much other things that still aren't where you need them to be providing those benefits. Contrast that with all the same needs that you have for your home remodel, but you aggregate all that into an overall project for the entire remodel of your entire home. You still identify all those things you need to change or upgrade and things you need, but you likely hire a general contractor and other professionals to come in and look this over, aggregate all that into one project, sequence the trades that come in and take apart to do the individual parts and work streams of that. That minimizes any rework. It is still disruptive and inconvenient for your family, but it has an end. And when that general contractor walks out the door for the last time, you and your family enjoy all the benefits and things you were trying to accomplish at that house remodel. It's one and done as opposed to seemingly go on forever. And just like the remodel that I may do versus Justin, each one is different. And you'll see that for our substation projects where they're individualized for those substations and circuits within the MYRP projects. We'll take a look now at the sample project there. This is actually in our coastal zone, and this is area 282, which is the greater Wilmington area. You'll see that it's made up of 21 geographically clustered substations, and their names are listed down the left-hand side of this table. You'll see the ones at the bottom have the word Wilmington in them. Again, that's the greater Wilmington area, including outlying areas as well. Across the top in the blue headers, you'll recognize those 10 categories or column headers as the programs that I described briefly earlier, and we'll go into more detail with the program summaries. I put a box around one of the substations there in the middle, Murraysville, and you'll notice that out of the 10 programs, there are only 6 selected for that substation. And the reason for that is there are not any capacity needs or self-optimizing grid needs in the next 3 to 5 years for Murraysville substation. That work has either already been done previously, or it doesn't show up in our cycle planning until after year 5. So it's in those out years that we'll catch in a future cycle from that perspective. You'll see other variability across the other substations listed within this MYRP project. And again, the same application applies. The analysis was done. The work is not needed at this time. And where you do see the check mark, there is a roll-up of that type of activity on that substation. I'll reiterate again here what I said earlier, that really we're looking for these projects in that 3 to 5 year timeframe. What are the critical grid capabilities needed then? Not out to as far as we can see with the Morecast tool into 10 years. This is focused in on the front half of that planning horizon. One last comment I'll make while I'm on this slide. The maturity of the estimates that we have in our file materials for this technical conference. These estimates are all as of early June. We certainly are facing other economic uncertainties, and as we refine our estimates through our process, we'll make sure through the appropriate vehicle to make sure the commission and all stakeholders are informed of what those changes are if some of these do change going forward. All right, we'll now move into the program summaries. And as I talk about each one of these programs, there's 2 slides for each program. The first one will be a program overview, like you see on the screen here for capacity. There'll be a second slide for each one that focuses on the benefits of doing that particular work, or work stream. Also you'll see, well, let me talk about this first and I'll touch on it before I leave the slide. Capacity upgrades are not new, but as I described earlier, the new layers and areas of capacity that we've got to look at are electric vehicle adoption as well as distributed energy resources and the two-way power flow necessary to accommodate those. That is all part of, as I've mentioned a couple of times earlier, part of the Morecast data that's leveraged for the capacity analysis for each of the circuits that we look at. There's also the automated distribution planning tool set, which is part of ISOP. That includes automated solutioning, which allows us to analyze, or a planner to analyze, not only at that circuit level for the individual thermal overloads that are identified, but also in that area, adjacent circuits and substations, leveraging that Morecast peak data on how to best alleviate that thermal overload. And that may include balancing load transfers to other permanent load transfers to other circuits, conductor and device upgrades, which are more traditional capacity implementation, as well as non-traditional solutions also. You'll see in the program description box, you'll see 2 different headers, retail capacity and system capacity. And I want to take a moment to explain what the difference is for those, or difference between those are. They're both necessary for the same reasons, to support traditional loads as well as DER and electric vehicles. The retail capacity work refers to upgrades or work done on our transmission to distribution substations. We call those retail stations because they are the substations that serve distribution's retail customers, as opposed to transmission's wholesale customers that they serve from other types of substations. The work that would be included for retail substations would include transformer upgrades or new transformers within the substation. It may include breaker additions if a new distribution circuit is needed outside of the substation. And it could even be a net new substation in an area that's growing quickly and serving that load center from other stations that exist in that area is not practical from that perspective. So think of retail capacity work as work inside the substation fence. System capacity is really the opposite of that. It is work outside the substation fence on the distribution lines, again, serving the same types of capacity needs. And this would include upgrades to wires and or equipment, as well as new circuits to serve growing load in certain areas. So retail capacity is inside the fence, system capacity is outside the substation fence. In each one of the program overview slides, you'll see estimated construction on the right, estimated construction timelines, estimated in-service dates, as well as projected costs. And in the bottom half of that box, you'll see critical grid capabilities critical grid capabilities enabled. And that refers back to the 4 that I talked about earlier: capacity, reliability, voltage regulation, and automation and communication. And then lastly, in the bottom, House Bill 951 policy considerations that are also addressed. I won't spend much time on those. I'll focus on what the program is as well as the benefits for each of those. So let's talk about the benefits for capacity, reliability, resiliency, and expanding solar renewables. Without doing proper capacity upgrades, we risk failures of overloaded conductors and equipment at peak times. Therefore, building in the necessary capacity in advance at the right time reduces potential outages from those conditions. Capacity improvements also help from a resiliency standpoint. While it certainly can be leveraged for the traditional means, it also provides alternate paths for switching and other redundancy when we have impacts to the grid. And I've mentioned a couple times already, capacity enables two-way power flow, which thus supports additional renewable energy resources as we transform the grid to more carbon-free sources. So self-optimizing grid, I mentioned earlier, this is a cornerstone program for distribution and addresses actually multiple critical grid capabilities. If you go ahead and look to the lower right, you'll see that 3 of the 4 are addressed by this singular program. And that's the reason I call it a cornerstone program for distribution. It addresses not only reliability, but also capacity and also automation and communication as well. As we're scoping and identifying self-optimizing grid needs, this is an area also that specifically the planning engineers leverage the ISOT tool sets, such as advanced distribution planning, and there's even a SOG automation portion of those ADP tool sets that also provides suggested automated placement of those switching devices along the circuits that they're studying. The planners still review that to see whether that makes sense or not, but they are presented with automated solutions based on the criteria for self-optimizing grid. There's 3 major components to self-optimizing grid. You see those listed in the program description. First off, capacity. So you may be thinking, okay, we just talked about capacity and you're talking about capacity again. So let me explain the difference between the two. The previous capacity that I spoke of is what is going to serve what I'm going to call native load for a particular circuit. So in the normal situation, this is all the load that circuit has to serve, traditional EVs as well as DERs. Self-optimizing grid, the purpose of that is to have 2 circuits or more that provide backup capability to adjacent circuits. So it's not only does circuit A have to serve all of its traditional load, if circuit B has a problem, circuit A needs to pick up some of those customers and pick up some of that load. So that's additional capacity for what I'll call emergent conditions or impacts to the grid, not just that native load that's on the circuits. The same analysis occurs, and the planning engineers are actually looking at both of those at the same time. And one is not doing multiple work. It's the same work, and it either will solve both problems or they're trying to solve one. But they look at that together for both so that we're doing it one time and one time only. Connectivity. I talked about the 2 circuits needing to back each other up to be able to perform that. They have to be physically connected with a strong tie to transfer load back and forth in outage or fault conditions. And lastly, the automation and communication. This is about applying those intelligent switches out on the grid, also the automation software back in our control centers that provides command and control, usually in less than a minute when it detects a fault situation, to restore as many customers as possible for that. There is a schematic in the middle of the diagram, or middle of the slide at the bottom. I think it's much easier to see in the detailed program summary. Let me describe what that is. That's actually a schematic for an actual self-optimizing grid in our DEP North Carolina territory. This one is actually in just adjacent to the Asheville Airport, so it's in the western part of DEP's territory. What you'll see is toward the top of that picture, there's 2 circuits that originate from one substation. The one that goes down and to the left is the airport road circuit and serves the Asheville Airport and surrounding areas. There's also one that goes down and to the right, and that serves the Fletcher area to the east of the airport. What this is indicating, you'll also see several boxes or squares. Some are a couple of green, some are red, and some are a red crosshatch. Those represent the automated switches that have now been placed on those circuits as part of the self-optimizing grid. Also, you'll see what looks like a cloud and a lightning bolt kind of in the upper left toward the center. That's indicating between those 2 green boxes that we actually have a fault condition on the circuit. And in less than a minute, the system has determined where that fault is. It's opened those 2 green switches. Green means open for us. And then closed all the other appropriate switches to restore as many customers as possible. all in less than a minute without human intervention. The operators in the control room are aware of what's happening and can take additional steps as necessary, but that's what the self-optimizing grid does. And one last piece of information here. So between those two green switches that you see where the fault is, there's 488 customers that have a sustained outage until a crew can respond, find the problem, and fix it. Before self-optimizing grid was placed on these two circuits, that same fault event would have resulted in 2,691 customers having a sustained outage. So from 2,691 customers with a sustained outage to 488. That's what self-optimizing grid can do for us and for our customers. So one other analogy I'll share here is if you think about the grid of the past, and Justin had a slide that talked about this. Think about a bicycle wheel. You've got the hub and you got spokes going out to the wheel. That's a very simplified representation of what the historical distribution grid looked like. You can think of the hub as being centralized generation or substation, and then the circuits go out to serve the traditional loads. Now think about a spider web. Spider web still has a center. It still has those radial spokes that go out to attach to the door frame or the tree limb or wherever the spider built it. But there's also dozens, if not hundreds, of connections between each of those spokes all the way around the grid. That's the type of interconnectivity that's necessary in the future to be able to support distributed energy resources. Multiple pathways to move power and restore power if needed across the distribution grid. Let's talk about, I've talked about benefits, but we'll go to the benefits page for self-optimizing grid. Certainly reliability and resiliency in this case go hand in hand. One, we're preventing sustained outages from a huge number of customers in that example, but also the system itself is able to take a punch and respond quickly, a fault condition, and recover automatically as many customers as possible from a resiliency standpoint. I mentioned again or earlier that it supports solar and renewables because we are building capacity for emergency backup. That same capacity can be used to move distributed energy resource generation around the distribution grid. And lastly, at the bottom, you see the benefit cost ratio of 5.5 for the self-optimizing grid work. So voltage regulation and management, this is specifically work to address the grid capability that I described earlier of managing those fluctuations. And as I said earlier, voltage regulation is not new, but the impact of DERs as the penetration becomes higher and higher is to mitigate the voltage fluctuations that occur from generation moving from max to min as clouds pass over. There's really three levels to the program. I'll say three different types of work we do. The first is additional voltage regulators installed on the grid to be able to manage those fluctuations. But also for existing voltage regulators, we install new controls that are capable of determining two-way power flow. Current controls are built to look at the substation as the stiff source of power and only regulating voltage downstream of that. These new regulators or the new controls have to be able to look in both directions and properly mitigate voltage fluctuations. Capacitors. Capacitors are not new on the distribution grid. That supports or provides reactive power support, and voltage regulation and reactive power support work hand in hand to properly manage voltage levels on the distribution grid for that. But there will be additional capacitor needs as we move into higher and higher penetrations of DER. The new part of this is actually power electronics. Power electronic devices have the ability to both manage and control voltage as well as provide reactive power support and do that almost instantaneously. That is the new capabilities that are needed in the future. One, will have those rapid fluctuations from DERs, but also think about traditional regulators and capacitors were meant to follow load throughout the day, raise voltage and VAR support, and as the load came down in the evenings, move back the other direction. With intermittency, those maybe have the potential to chase voltage fluctuations during the day and always be following, trying to chase that. The power electronics can damp out those rapid changes and manage those, where truly the regulators and capacitors perform the more traditional function of increases as load moves up and down during the day from that perspective. One other way to think about that is think of capacitors and regulators as the coarse voltage and reactive power adjustments, and the power electronics give you that not only fine adjustment, but also instantaneous adjustment to deal with those fluctuations. So let's talk about the benefits for voltage regulation. And this is really about maintaining proper voltage levels. We are required to maintain voltage as part of our obligation to serve within certain prescribed limits. This allows us to maintain and continue to do that even with the intermittency and voltage fluctuations introduced by distributed energy resources. That improves the the voltage experience for customers and maintains what they experience today. By doing and applying and doing this work, we're able to support additional DER penetration on the grid as well as what is there today. And then by properly managing voltage, if customers have any concerns about the ability of us to deal with growing electric vehicles or DERs, we'll have this capability there ready for those customers. That will not be part of their concern as they choose to make those kind of choices in the future. And certainly this helps with two-way power flow and properly managing voltage in that case to prepare the grid for a lower carbon future. So hardening and resiliency, there are three different areas that I'll talk about in this space. The first of these is laterals. And let me make sure and draw a distinction between laterals and the backbone on the distribution grid. I think you can think of transmission, I think Dan would agree with this, as the interstate highway system is what transmission is. There are superhighways and others, but all call them limited access highways. When you think of the distribution grid, think of 4-lane, more urban highways, or maybe they're even rural highways, but they're not limited access. And then all the side roads that go off of those main roads. The laterals, when you hear me say laterals or tap lines, I'm talking about the side roads. It's the smaller portions of the distribution grid where most of our customers live. But then we'll have also programs that work on the backbone. SOG is an example of one that's focused on the backbone. This particular program, the reason I draw that distinction is it's focused on the laterals. One of the things to keep in mind, if you remember my reliability description early on of not just traditional impacts of reliability, but now we're impacting an outage impacts generation as well as electric vehicle charging. Most of our customers live on and are connected to the grid on the laterals. Many customers are on the backbones, but the vast majority are connected via the laterals. So the lateral reliability takes on a new dimension as we move forward with the grid of the future for that. This is a data-driven approach looking at outage history and very specific cause codes for the outages on those laterals, as well as a review of the physical condition of the wire, typically looking for damage or potentially multiple splices with indicating that the line has failed before and been spliced back together. What we most commonly find with this program that needs to be addressed is an older vintage steel core wire. It was a high strength wire, an older vintage of material, gave us high strength, but over time, that steel core that provided the strength presents a corrosion risk. And as that corrosion risk increases, there's potential failure in those particular cases. Our standard, modern standard now is an all aluminum high strength alloy that we deploy in new construction. These laterals would simply be upgraded to our current standards with that high strength all aluminum alloy for that. One other comment I'll make here is as I go through the rest of these program summaries, early on we had programs that were focused on capacity, focused on voltage regulation, and then of course self-optimizing grid covered 3 of the 4. The rest of these will all focus on reliability, and the reason for that is what I've described. The impacts of an outage now now and in the future is also on generation as well as electric vehicles. So the benefits of hardening and resiliency for laterals, reliability and resiliency, eliminating the risk of outages, increases the reliability, improve resiliency. A modern high-strength conductor provides the ability to withstand limbs falling on it and others that an older conductor with a corrosion risk may not support as easily. And then upgrading historically outage-prone assets lessens the quantity and duration of outages, so overall system resiliency and reliability increases. Anytime we avoid an outage, that bends the restoration cost curve down for all customers. And then a reliable and resilient grid is certainly necessary for distributed energy resources in the future. And lastly, the benefit cost ratio you see for this work of 9.4. So the second part of hardening resiliency is public interference. And public interference is a utility term that we use to indicate anytime a non-utility worker has impacted the facilities, whether it be just damage or causing an outage. It may be a contractor digging that hits an underground cable. In this particular case, what we're focused on is vehicle accidents where we have cars hit pole. For any of you that watch the news, whether you live in it or just watch the news in one of our metropolitan areas, Raleigh, Charlotte, Greensboro, High Point, others, likely several times a week during the morning news, either the traffic reporter or some live on camera reporter is reporting on a vehicle accident that's damaged Duke Energy's facilities. And typically it's broken a pole. There's a large outage in the area and traffic is probably impacted for several hours as they attempt to make repairs in that case. So not only is there the impact to the customers that are actually experiencing the outage, there's societal impacts impacting commerce from transportation and traffic rerouting and other things of that nature. So in this particular program, we're focused on those areas where we see with our data now that we've got repeat hits in certain areas. And also this is focused only on our 3-phase, so the most impactful types of events where we have car hit pole. The solution set would include potentially design change, a relocation of the existing facilities, or potentially undergrounding to remove them from the line of fire from particular repeat vehicle accidents in those particular areas. So we'll talk about the benefits. And one of the first things that I'll point out is the benefit cost ratio is less than 1. And let me talk about that. So the benefits are reducing or improving reliability and resiliency by relocating facilities, avoiding an event, and making the system more ability to withstand any kinds of impact. But with the benefit cost ratio, we believe this is prudent utility practice. We've got data that now shows, and we can track where vehicle accidents occur on our backbone systems. And there's also, as I mentioned, besides the pure reliability benefits that go into the cost benefit ratio, there's the societal benefits and impacts on commerce and just traffic in general in those particular areas where this occurs frequently in those areas. You'll also notice that overall, compared to the overall MYRP projects that we're proposing, this is less than $16 million, so very targeted to areas that we see areas for improvement in that particular space. So distribution hardening resiliency storm. So the last of the hardening and resiliency. This is also a data-driven looking at outage history, but very specific storm cause codes, and also a geographic analysis looking at more of our coastal areas and mountains to look at potential tropical impacts, as well as winter type weather, icing and others. There's a lot of information there in the program description, but at the heart of it, it talks about grade B construction and NESC 250B to D loading. What the simple boil down of that is, what that analysis results in is where in these areas where we have propensity for higher winds and heavier ice loads is larger and stronger poles, shorter spans between those poles, and additional guying to support those structures in the event of high winds and ice loading, where we've seen it happen repeat again and again in those areas for that. So moving on to the benefits, again, reliability and resiliency. The grid itself being stronger, able to withstand higher winds and heavier ice loading is the definition of resiliency. Also, by reducing the risk of outages caused by those potential severe weather events, we're improving reliability. Outage cost avoidance, any outage that we prevent bends the cost curve down for all customers from a restoration perspective. And certainly a more reliable grid supports additional DER and EV adoption. And you see the benefit cost ratio of 8.7 for this work. Distribution automation. This is an existing program. It modernizes traditional protective devices on our laterals. So again, this is a program focused on the laterals, not the backbone of our distribution circuit. And this is accomplished by replacing a traditional single-use fuse with an intelligent electronic device or automated lateral device. You see an acronym there in the middle. Is really a modern recloser for a single-phase device and fits in the same location that a traditional fuse was. I'll share another analogy here. If you think about, I mentioned your grandparents' car and what the modern technologies that it had or didn't have. Think about an older home with a fuse box, not a breaker panel, but a fuse box. And if you lived in a house like that, my grandparents' house had one. When the lights went out in the bathroom or the kitchen, somebody had to go to the back porch where the fuse box was, open the panel, look for the blown fuse. There was probably a box or 2 or 3 boxes of different size fuses sitting on the shelf. You unscrew the other one, just like unscrewing a light bulb, screw the new one in, and the lights came back on if the fault or the problem was temporary. What I'll also make sure that I want to say here is that most faults on overhead systems for distribution are temporary faults. A couple of examples. It may be a limb that's falling from a tree, temporarily brushes the line, and continues to fall to the ground, or it may be an incidental animal contact. Those also tend to be temporary faults on the system. The challenge with that traditional fuse, just like the fuse in your grandparents' fuse box, is if the fault magnitude is high enough or it's just long enough, potentially the fuse does what it's supposed to do. It opens up and protects the lines or the circuit from further damage. But it's a temporary fault. So we now have customers that are experiencing sustained outages based on temporary faults. With these automated lateral devices, they can actually reset themselves. So they will sense the temporary fault. They may open up and de-energize the line, but in a couple of seconds, they will close back in. And if it truly is a temporary fault, The customer saw a blink, but nobody has a sustained outage at this case. So that's the value of these devices. You can kind of think about your modern breaker panel that you have in houses of today, but you still have to go out to that breaker panel and turn it off and turn it back on to reset it. These devices do that on their own. There's no human intervention needed. If it is a permanent fault, it will operate and end up staying open, and there'll be a sustained outage, as it should be for a permanent fault. But temporary faults no longer, in this case where these devices are deployed, cause sustained outages. And again, we talked about reliability being one of those critical key grid capabilities based on generation as well as electric vehicle charging. The benefits of reliability and resiliency again, and you see the cost benefit ratio for this work of 5.1. Equipment retrofit. This is also an existing program. It targets equipment prone to outages caused really by three things: lightning, overvoltage, clearance issues, or animal interference. And it really upgrades those assets to our modern design, construction, and material standards. The types of equipment, I mentioned this earlier, that we focus on with this program are transformers, arrestor locations, and riser poles. And remember, riser poles are where our system transitions from overhead to underground. It's that last pole where that transition occurs is known as a riser pole. The work that we do at these locations is similar in each of the three examples or asset classes. We install, number one, local fuses. That way, if there is a problem at that device, only the customers served by that particular asset experience an outage. Without those local fuses, the outage is further out to the next protected device, and customers that don't need to be out based on that failure experience an outage right now. We also install animal guards and covered lead wires that mitigates animal interference. And also specifically for lightning arresters, whether they're on a transformer or an arrestor station, we replace older vintage porcelain lightning arresters with modern polymer lightning arresters, and that increases the insulation levels on the distribution lines at those locations. And lastly, we replace conductive metal brackets with non-conductive, typically fiberglass brackets. Again, that helps with clearance issues as well as animal interference and other clearance issues on those locations. Benefits, like the others, improve reliability and resiliency, reducing the number of outages. With those improvements of construction and design standards and materials that we made at those locations, they're able to mitigate animal interference and withstand those contacts without causing an outage. Outage cost avoidance from fewer outages, again, for all customers, bends the restoration cost curve down. Certainly improve customer experience for those customers that are served by these assets as they're brought up to modern standards. And lastly, you see the benefit cost ratio for this work of 3.0. Moving on to long duration interruption. This is another existing program, and it relocates segments of our overhead circuits. This is focused on the backbones as opposed to laterals. So this one is again focused on the backbones, and moving those facilities from hard to access areas to more truck accessible areas. That certainly reduces outage restoration time and also allows for ease of maintenance to reduce future outage risks when they're easily accessible by mechanized equipment. The targets that show up in this program are typically, number one, they're typically radial distribution lines that serve either large groups of customers or maybe entire communities that tend to be geographically isolated. And it doesn't make sense from us from a cost benefit ratio to build an alternate feed from another direction because they're isolated geographically. So the best thing that we can do at this time is move those lines from inaccessible areas such as off-road, swamps, mountain gorges, or other extreme terrain. And they also have typically higher than average outage durations because it's radial, and then the lines are inaccessible. It takes our crews longer to respond, find the problem, and make repairs. Then you layer on top of that extreme weather. If these are in a swampy area and we've got a tropical type of severe weather event, that just exacerbates accessibility and to get to that equipment. Same thing in the mountains. If you're in a mountain gorge or extreme terrain in the mountains and you have an ice and snow event, again, because they're not truck accessible, extremely difficult to get to. And the solution for these is really to move those to road right of way or truck accessible areas. The benefits, similar here, reducing those outage risks. So reliability, resiliency, bending down the outage cost curve by reducing the number of outages that occur, and also more shorter outage durations in those extreme events or when they do have one because it is truck accessible. This not only bends the cost curve down for outages that don't occur, but the cost of restoring in those extreme terrain areas typically is much more manpower than traditional, very specialized equipment, to get in there. And we can do that. If we move those to road right away, we can leverage our standard equipment and access from the roadway and repair much quicker in those cases. You also see the benefit cost ratio 14.0 for this particular body of work. Targeted underground, another existing program. This one's also data driven. This one focuses on our laterals. So back to the lateral parts of our system, strategically identifies in undergrounds the most outage prone overhead line segments. This reduces not only the outages for those customers served by those line segments, but once we've undergrounded those, they typically are in heavily vegetated areas in rear lot. It eliminates that vegetation management cost in the future when those lines are placed underground. The attributes that typically show up for these targets, unusually high outage frequency. The location of the lines currently is typically rear lot, built behind houses and inaccessible to mechanized equipment. And typically over the years, those have become heavily vegetated, even if they weren't when the lines were originally built. And the solution for these is to move those to the road right of way or front lot, and also underground those lines as well. Also for this program, no surprise, reliability and resiliency are key. By putting lines underground, certainly less susceptibility to weather impacts, at least in major events and normal storms. We've also eliminated, as I said earlier, that vegetation management cost and also the restoration cost. Those lines are much easier to access and restore, being moved to the front lot line. Again, we don't have non-mechanized outage restoration happening behind homes. And again, the laterals are where the majority of the EVs and distributed energy resources will show up as we move into the future. And so that lateral reliability is even more important. And lastly, you see a benefit cost ratio of 7.0 for this work. So hazard tree removal, and then I'll finish with infrastructure integrity. Hazard tree removal, I've described this earlier, but want to reiterate. This is part of our integrated vegetation management program. One portion is focused on vegetation management within our prescribed rights of way. An example may be a 30-foot right of way for distribution lines. So our lines are in the center and we maintain 15 feet either side of those facilities. This work is not focused inside the right of way. It is very specifically and limited to the outside the right of way. And what our specialists are looking for is dead, diseased, dying, or otherwise structurally unsound trees that if they fail, would fall toward the distribution lines and cause impacts to our system. And I'll also say, vegetation within the rights of way typically is smaller vegetation. It's limbs falling, et cetera. Many times it doesn't actually damage our facilities. It just causes an outage. But at most, it typically would just break the wire. You have a tree falling from outside the right of way. It is not only going to take the wire down, it likely is breaking a pole or multiple poles that now have to be replaced. So we have infrastructure replacement to do before we can even begin restoration in those cases. And to talk about the impact of trees falling from outside the right of way, for DEP North Carolina, the last 5 years, 2017 through 2021, every single year, more than 50% of our vegetation outages were from trees falling from outside the right of way in that case. So heavily impactful from that. And again, this is all outside of our right of way. The way we accomplish this work, a Duke Energy representative specializing in vegetation practices leverages industry best practices to identify those dead, diseased, or dying or structurally unsound trees. If they do discover an extreme risk to infrastructure that is an imminent failure, they will assign that to a vegetation supplier to immediately take that tree down. But the vast majority will result in a list of hazard trees and locations presented to one of our vegetation suppliers. They make contacts with the customer, explain the work, receive consent, and then schedule to take those trees down on a particular schedule. And the benefits for this, again, reduces the risk of outages. And I described how impactful that has been over the last 5 years for DEP North Carolina from those trees falling from outside the right of way. This is a prudent utility practice and we've been doing this for years to remove those threats that we identify outside the right of way, as well as properly maintaining those inside the right of way. And lastly, infrastructure integrity. I talked about this a little bit earlier, but back to that house analogy, all the other programs I've described they're more like the house remodel. They're looking above the ground. It's things that we need to add to the grid and improvements we need to make there. But we also have to look at all the infrastructure that's served or part of these MYRP projects and make sure the foundation is in good condition. Same thing for that remodel. You wouldn't do all and spend all those dollars to improve everything above the ground if you've got a failing foundation or problems that need to be addressed before doing that work. Some examples of this you'll see in the bottom in the program description. That would include inspection-based asset replacements, could be transformers that have been inspected, as well as poles. Oil mitigation, where we have opportunities to upgrade equipment from hydraulic to solid dielectric, removes oil off the system. Distribution does have some SF6 gas insulated switchgear. Those are typically vault-mounted switchgear that we now have the option to replace with modern solid dielectric, so we can remove that SF6 gas from the distribution grid. Technological obsolescence, that's one that's listed there. That one specifically says recloser controls, but that could also apply to regulator or capacitor or other electronic device on the distribution grid that have a control panel. And the obsolescence could be a couple of things or multiple things. It could be one that doesn't fit our cybersecurity requirements now. It could also be one that the vendor is no longer supporting. It's actually functioning, but if it fails, we can't find parts or do any replacement. And so we would upgrade that to a modern. Or the example I gave earlier of technological obsolescence for voltage regulators. The current controls cannot control voltage in two different directions. They're simply looking from the substation out to control voltage. The modern controls can determine a stiff source from either direction and properly maintain voltage. And there's a couple of other examples listed also. And lastly, the benefits for infrastructure integrity. Again, reliability and resiliency. It reduces the risk of outage due to unplanned replacements or failures. Sustained infrastructure integrity enables more efficient restoration when there is an event that we need to deal with. Oh, sorry, I lost my train of thought for that for a second. Also for the customers and the experience, having planned replacements of these assets is much less impactful than unplanned events, whether it be an outage or doing those individually. We do those as part of our overall MYRP projects. As I stated earlier, we mobilize in, uplift the infrastructure, including this work, and then move on to the next area. That concludes the distribution projects. I'll now turn it over to Dan Malley to talk about transmission projects.
All right, why don't we pause here and let me check in with commissioners to see if there are questions for Mr. Guyton on his presentation. All right, Commissioner Gladfelter, go ahead.
I have several questions, but they're not specific to distribution. But Mr. Guyton, I've got one for you that is specific to distribution. And let me preface the question with a comment. Way back in the dark ages before the pandemic, I remember the technical conference at which you came in and presented the plans for ISOP. And I wanted to just say to you that listening today to some of what you went through is a really good feeling to see what's come to fruition over the course of the last 3 years as you've implemented the ISOP initiative. And to see some of the fruits of that today is good. I appreciate it. I remember when you were just starting the journey, and it's good to see the progress you've made along the way. The question really relates to the capabilities of Morecast and how it works. And I'm really intrigued about how when you're sort of running a Morecast forecast on a circuit and try to identify sort of the 3 to 5 year needs on that circuit for various investments on the circuit. You tell me if I'm wrong, but I'm assuming that within Morecast, you're not able to model endogenously within Morecast the adoption rates of EVs on a particular circuit or installation of rooftop solar or other DERs on that circuit or that substation. Morecast can't do that modeling, can it?
There are some, it's a good question. There are some assumptions made, and I don't know the absolute details of the algorithm, but it does look at certain factors that an area would be more prone to adopt EV or rooftop solar. Again, I don't know the gory details of that, but it does assume, based on customers and other things, of who might be and what areas might be more prone to adopt faster in those cases.
Well, that's intriguing, because that's really, you're getting at the heart of really what I wanted to explore, was whether or not you provide a sort of a certain level of EV adoption and a certain level of rooftop solar within the service area of a given substation, and just provide that as an external input to Morecast, and then say solve for that level of DER and EV adoption, or whether the model itself can generate some of that.
So my understanding is there are multiple data inputs into the model that then it calculates what that propensity to adopt EV or solar is, as opposed to just having here's the EV number, here's a DER number from that. But I don't know the detailed specifics of the algorithm that does that.
Wow, that's really interesting to hear. And so it leads to a follow-up question, which is, do you then feed those results upstream to your resource planners and say, look, when we run Morecast across the distribution grid, we're seeing this rate of EV adoption, and you should expect this many EVs on the grid within 5 years' time. Do you share that information with the resource planners?
Yes, and actually Morecast is part of truly the ISOP tool set. So it's part of ISOP. The planning engineers actually leverage that for load forecasting for individual circuits. So it's actually the critical part of it is to inform the overall integrated resource plan. We're leveraging, like I said, the first 5 years of that forecast to look at actual planning for distribution projects, infrastructure projects that need to be executed.
Outstanding. So let me ask the ultimate $64,000 question. So then when I read the IRP or the carbon plan, which we're currently reading, either one of them, when I read those documents and I see a sort of a projection of how much rooftop solar is going to be out on the grid over the course of the planning period, I can say that's an output, in large measure, it's an output from the forecasting process.
I was not part of the carbon plan development, et cetera. That would be my assumption, but would need to be validated, but I would expect that.
That's very interesting. Thank you for that. That's very helpful. That's my question. Thank you.
All right, additional questions. I'm unable to see Commissioners Duffley, Brown Bland, and Hughes. So if you all have questions, you need to let me know because I can't see you right now.
I have a question. It's Kim Duffley.
Okay, go ahead, Commissioner Duffley.
So you may hear from other commissioners asking about SAIDI and SAFE, but in the presentation, I heard a lot of benefits regarding reducing outages as well as the length of the outages. And so my question is, what are your current SAIDI and SAFE metrics right now compared to your past two rate cases? And, generally, are they trending up or down?
Commissioner, off the top of my head, I don't have that information in front of me. I think I can specifically for self-optimizing grid, that has a substantial impact on reliability. There's a lot of other impacts, so I don't know the overall system numbers and how those are trending at the moment. But the impacts of, if just as an example, for the self-optimizing grid work that we're proposing to execute in this time period, we expect, I'm sorry, I'm looking, I have a number here that I captured for this purpose. An additional 21 million customer minutes of interruption saved just for the self-optimizing grid work that we're proposing within this MYRP plan. So I apologize for not having the reliability numbers tied to the rate case time periods, but quite a bit.
That's okay. We can find them. I just wondered if you knew off the top of your head while we're talking about it today. So thank you for that answer. And then my one other question is, when you went over the infrastructure integrity program overview and benefits, and you may have said this and I missed it, but most of the other ones had the total benefits, gave that benefit cost ratio, and this program did not have that. And what is the reason for not having it with this program?
Yeah, thank you for asking. So infrastructure integrity is work that we see that as an obligation to serve as a utility to maintain the foundation, whether we're doing other reliability improvements and things above the norm. This is simply maintaining that foundation. And so I guess the example I would give is if I have, kind of back to my analogy earlier, if I'm going to do that house remodel, but I've got a foundation issue, I certainly may get different bids from vendors, but I'm not going to not fix the foundation. It's just work that I have to do from that perspective. I wouldn't do a cost benefit of, okay, if the foundation fails, here's what'll happen versus spending the money to fix it. I've got to fix it from that perspective. So that was the reasoning there.
Okay, that makes sense. Thank you. I have no further questions.
Thank you.
All right, additional questions. Commissioner McKissick.
Sure, just one or two. In looking at your cost benefit ratio, I mean, of course, it varies from project to project. Some may be down at 0.5% or others up at 8.1. What methodology did you use for establishing the cost benefit ratio for these particular projects? And I guess that question also applies to ones that we're going to get into later in the next section of the presentation. I mean, could you elaborate further on the methodology that was used?
Yeah, absolutely. So I would offer overall, we leveraged a similar methodology to we have in the past.
Okay.
And at the core of that is the ICE calculator, interruption cost estimating tool. Based on feedback from this commission and staff previously from those other filings, we not only used the ICE calculator, but also specifically using the online version, created our tables specific for North Carolina, as opposed to the standard tables that are part of the ICE calculator. And those went into our traditional cost benefit analysis tools of here's all the costs we have, here's the benefits, not only from the ICE calculator, but our cost to restore the outage and other factors such as that.
So is the ICE calculators and specifically the ratios applicable to North Carolina?
That's correct. We generate from the online tool. You can go in and actually pick the state. I can't remember the other criteria that's there. And actually it will generate values that then we specifically took those values and put them into our CBA analysis tool set.
Thank you. Did you consider employing or utilizing any other tools or methodologies for calculating cost benefit ratios?
Not that I'm aware of. The ICE calculator is the only one that I'm personally aware of that's an industry accepted. It was funded by the DOE. They're going through some updates, I think, to the tool now that we'll probably see maybe in 2024, 2025, including more utilities, different surveys, and updated data from that. So that's the only one I'm aware of, but that is what we use, sir.
Thank you. And I guess the other question is kind of a follow-up to what Commissioner Clodfelter asked you. The thing I'm trying to determine when you're looking at, say, adoption of EVs or adoption of rooftop solar, at least for rooftop solar, we have a pretty long established track record. For EVs, it's not so great. How do you sit back and extrapolate what that adoption rate might be, particularly since it could be linked to other external factors that you may not have control over, like the price of a barrel of oil?
Yeah, good question. And I guess I'll have to answer the same way I answered Commissioner Clodfelter's question is, I don't know the details, but it does look at multiple factors and incorporate those of what may drive someone to select an EV. I don't know if it looks at economic data of household income and other statistical information, but leverages that to look at both historically, where you've seen DER adoption, what tended to be the drivers there. And I think they're making some assumptions, of course, and trying to model what do we think the EV piece will be like based on the best data that we have from that perspective.
Thank you.
What, Commissioner Clodfelter?
Yeah, let me follow a little bit on one of the questions that Commissioner McKissick asked you. I was going to hold it till the end because it applies to transmission as well, but since we got the topic on the table, let me go ahead and ask it. In the company's last general rate case, public staff witnesses, Thomas and Williamson, and a couple of the intervenor witnesses made some very detailed recommendations about how Duke should revise and adjust its cost benefit analyses, changes to data sources and inputs, as well as changes to methodologies. Other than what you outlined to Commissioner McKissick, what other responses did the company make to those suggestions from the public staff witnesses?
Besides the one I specifically referenced of that very specific North Carolina table, I personally do not know what those changes may have been. I know there was a lot of discussion and intake of that into looking at how we would modify those. But that's the one I specifically know of. I'm not saying that others weren't done or addressed, but I do not know the answer to that question.
I predict that's going to be a topic of some questions in the rate case themselves. And so good to go ahead and get the question on the table for you today so everybody can be thinking about it. Let me ask you about one specifically to see if it jogs your recollection. The public staff suggested that the company run sensitivities to various to different variables used in the cost benefit analyses, and that was not done in the last series of studies that were presented in the last rate case. Do you know if in the current modeling of cost benefit analysis that you've got summarized in these materials where the different sensitivities were run on different variables?
I do not know for sure.
Don't know. Okay.
Yeah,
Again,
I can tell you, we did not run multiple cost benefit
Did not.
analyses for sensitivities.
Okay. Just forecasting questions for the general rate case. Try to help you guys out. That's all.
All right, Commissioner Kimmerite?
Thank you for your presentation. Just following up on Commissioner Duffley's question. In addition to the infrastructure integrity program, I also did not see a benefit cost ratio for the hazard tree removal program. Is there a reason why that program also does not have the ratio?
Yeah, great question. And really it's the same answer. This is an obligation to serve. We have a known threat to infrastructure, and the trees need to be removed. And I guess another analogy I would give is if I've got a tree leaning over my house that's posing a threat, it's dead, dying, or an arborist tells me it's dead, dying, or structurally unsound, I certainly may get bids from competitive vendors to take it down and choose the one I think is appropriate, but it won't be a cost benefit analysis of if I don't do anything versus doing anything. It's a known risk that we see that as an obligation to serve.
Thank you.
Commissioner Brown Bland, I see you on camera. Do you have a question?
No question.
Okay. All right, Mr. Guyton, I have a few for you. We'll stick with hazard tree removal since Commissioner Kimmerite was just talking to you about it. How does what you all have proposed here compare to what you all are currently doing with respect to hazard tree removal?
We're removing hazard trees now. This is simply
A continuation
a
of,
continuation of that work. We feel like it meets the requirements for inclusion in MYRP, but it is the process and what we do and how we do it is exactly the same.
okay, and level of spending would be similar to what you're spending now?
That to my knowledge, yes, we're
Okay.
doing that work now.
Okay. And did I hear you correctly, if I didn't, correct me, when you said 50% of vegetation management related outages caused that the company is experiencing now are caused by trees from outside the right of way?
That is correct.
Okay. Okay.
And that's not just the average over the last 5 years. Every single one of those 5 years, it is above 50%. It moves from, I think it was from 51 to 56%, but consistently it is over half of the vegetation outages.
Okay. Okay. All right. You also discussed today with respect to the capacity program, outages due to overloaded conductors. Is the company experiencing overloaded conductors from associated with DER penetration or customer load at this point in time, or is the company anticipating that?
Is the question, are we experiencing overloads or are we experiencing failures due to overload?
Well, overloaded conductors.
By our planning analyses, there are conductors that are technically overloaded.
At present, they're overloaded
At
conductors.
present. Specifically, I couldn't tell you or give you a specific example of this one's overloaded because of DER, but we are constantly looking at thermal overloads and then addressing those appropriately, whatever the drivers are.
Okay.
In capacity and in our forward-looking capacity, we are, as the other questions have come about forecast and how it views EV adoption and VDR, we are looking to create additional headroom or hosting capacity on those circuits and not get to an overload situation, even with EVs and DERs coming from that perspective. So that's if traditional planning was here, there's another layer of capacity here to be able to deal with those modern technologies and their impacts.
Okay. All right. Thank you for that. Some of the, as I have understood what you've described today, some of these programs would seek to prevent faults, and some of them would seek to mitigate the impact of faults. Like you described, the self-optimizing grid would mitigate the impact of faults on customers on the circuit. So how do you all prioritize spending on programs that prevent fault versus mitigate impacts of fault?
So what I would offer is that what we're proposing here is a comprehensive plan. So we're addressing both. It's an all of the above. One, we need to make sure that we can never build a grid that would never have a fault. That's not a practical thing to do, or couldn't afford it even if we could do it. And so we address both. Certainly, the intent is wherever we have identified ways to prevent faults and do that with a cost benefit analysis, make sure it's worth the money to do, we're going to try and prevent the fault first. If there's not a way to simply prevent the fault from ever occurring, let's make sure we minimize the impact to many customers. And that's why what you'll see is on the laterals, it tends to focus more on fault elimination or trying to prevent it from being an outage. Whereas on self-optimizing grid, we know we're going to have those things impact significant numbers of customers. And so while we still do work to try and prevent the faults, vegetation management, a lot of the equipment retrofit work, that will be on laterals and backbone circuits. Wherever that equipment exists, that's where we would apply that. And that is trying to eliminate faults as opposed to just preventing the impacts. So I'm not sure if I answered your question.
You did. The commission in the most recent rate case orders directed the companies to work with, I think it was Votes, I think this was at Votes Solar's request. Let me get my notes. It was Votes a stipulation that Duke entered into with Vote Solar to form a climate risk and resilience working group to identify vulnerabilities on the grid and potentially solutions for those vulnerabilities that result from severe weather impacts. Is any of this work informed by the work of that group, to your knowledge?
So I'm going to say no, but let me preface this with this. My understanding of that climate risk and resiliency study is looking further out in the future for threats into the future. And then once those threats are identified with that, I guess the first part of that study, then what would potentially be changed in design standards or other things for that decades out look. And so this work is focused on what we know now and what we do. So I'm going to say I'm not aware of any impact by this study.
I can add too that I've seen a draft report of that. I think it's going to be issued very soon. That the work that we have contemplated in for T&D is not counter to anything that's going to be found within at least the initial inputs from that particular study.
Okay. How are you all assessing weather-related risk the same way for the purposes of this nearer term activity versus perhaps the longer term analysis that the climate risk and resilience group is undertaking?
I'm not sure I'd answer that with a yes, but what I will say is that that storm hardening and resiliency that I just spoke of, recognizing the frequency and severity that we have of both winter and tropical events now, is looking very specifically at those areas that we've seen impacted repeatedly in the past, and then applying grade B construction and NESC ice loading criteria for those. I would not be surprised if in that climate study at some point it references, higher standards of strength for the grid because of future threats for that. So I think, as Justin said, it's in line with where we believe that study will go with, strengthening the grid. And so I don't see that being counter to it. I think it's supportive. We're out in front of it, again, looking at severe weather impacts.
Okay. And so as you, to identify severe weather impacts or severe weather risks to DEP's grid, what data are you relying on? How are you analyzing
So it
that
is
risk?
looking at the locations where we've had previous damage from tropical events as well as winter events, and looking specifically at the outage cause codes. If it's a storm outage cause code, the dates line up with when we had one of those major events, because those typically are major event days. We have that data to look at and say, where do we see damage? let's assess those areas and see if it needs additional strength for ice loading or high winds from tropical events.
Okay, thank you. That helps me. Several commissioners have asked you about benefits, program benefits. You've discussed them at length here today. In some cases, they've been quantified. The more I'm curious and ready to learn more about how the company is identifying benefits and quantifying them. So the more that the company can help me as a commissioner understand that how you're identifying benefits and quantifying them would be much appreciated. That was a comment more than a question. All right, let me just look through here and see if there's anything else I want to ask you. All right, maximum ambient temperature. Is the distribution system designed to maximum ambient temperature for optimal operation at this point in time?
I know that in our conductor ratings, air temperature is taken into account. I don't know if they look at maximum ambient or not. I'm not a standards engineer.
Understood.
There is temperature, variations based on sag, because that's how we develop our spacing on the poles.
And do you anticipate that changing ambient line ratings or you're taking into account of temperature ranges?
I'd be curious. I would think that climate and resiliency study is going to point to things of that nature of if they truly are identifying a change in temperatures, that would be incorporated because we would assume our normal temperatures are greater, but I don't.
Well, I don't necessarily, I mean that for purposes of your operations, allowing your sort of greater temperature fluctuations for purposes of your operations.
I do not know, but I would think that would be taken into consideration both for operational
Okay.
practices as well as design standards.
Okay. So it's not something that you all are considering right now is what I'm taking.
It is not part of that. We
Okay.
are leveraging for this work, our current design and construction standards for this work.
Okay. All right. And one last question for you. And this is mostly to make sure I'm reading this correctly. Back to the hazard tree removal program. Are you all proposing to capitalize certain expenditures associated with that program?
Yeah. Work inside of our maintained right of way is O&M cost to maintain that. Doing work or expanding, not really expanding the right of way, doing outside is capitalized. I'm not an accountant, but that's my understanding of how that work is treated outside the right of way versus inside.
Okay, so to the extent that these costs are shown as capital costs, it would be due to the fact that work is being conducted outside the company's right. Okay.
Correct.
Okay. All right. Go ahead, Commissioner Gladfelder.
Mr. Guyton, sorry, I didn't think of this earlier. I apologize. With respect to the LDI program, I'm reminded that one of the justifications, the principal justification for the Hot Springs microgrid was to solve an LDI problem, but I don't see that identified as one of the options for the LDI program. Should I draw any conclusions about the success or failure of the microgrid at Hot Springs, or is there some other reason why that's not an element or a potential option for dealing with LDI situations?
I don't think that should be taken as any reflection on Hot
Okay.
Springs. Things I've heard and seen from that. I'm not keyed in on that project, but things are moving along appropriately for it. In this particular case, I think Hot Springs had some unique abilities to take on that type of project. But certainly as we look at capacity or other upgrades like that, a non-watch alternative is part of our analysis in that. For the long duration interruption, it typically is not like a Hot Springs where you've got, I don't remember the number of customers, but that whole little village was impacted. These tend to be smaller, but they're the customers that see those every time we have a major event or there's an outage, even in blue sky days. It's long to get to them and get them restored just because of the access to the lines. Hot Springs had that challenge too. It was remote terrain.
So again, help me understand why that would not be one of the weapons in your arsenal for solving long duration.
I think it certainly could be, but for these, the cost of being able to relocate to the roadway was much cheaper than battery alternatives for these.
So these are, we look at these as really low cost solutions.
They're low cost, and I would offer, I'd have to go back and look at the projects. but the number of customers impacted is much less.
Is much less than in the Hot Springs
Yeah, Hot
case.
Springs.
So do you, I mean, where would I look, if I wanted to look in here to find where you're going to address similar situations or opportunities, I should call them, like the Hot Springs opportunity, which program would sort of
So
speak to that?
that actually be in capacity. So if we
In
have
capacity.
if we have capacity projects where traditionally we would propose a wires alternative, so typically upgrading wires or equipment, that's where we would do a non-wires alternative review for that. We've done some of those. We haven't had one that was the least cost opportunity or option to do those, but we're continuing to do that. And I would expect over time as if costs moderate after the global uncertainties in those spaces, that you would see those start to move into that space.
Okay.
But we are constantly leveraging our energy storage group, looking for places to deploy additional battery type assets.
Thank you, sir.
All right, last question from Commissioner McKissick.
Yeah, and this is just kind of more of a curiosity than anything else. I noticed in the distribution hardening and resiliency program, it refers to you planning using, assuming a grade B and an NESC standard of 250 BA. Why did you decide to use that as the standard as opposed to whatever grade A would have been?
So I'm not a standards engineer, but my understanding of that is a higher level of strength,
Okay,
grade B, than what our typical construction is. And then the NESC loading criteria, I think it was 250 B to D, that's actually looking at ice loading. And that's looking at, which our historical grid, we've not had that type of activity. We've always had some ice, but they're getting more severe, heavier applications of ice. So that's why we're looking at those areas saying, let's move up to a higher level of strength in those areas, whether it be for ice loading or wind loading. And that's what those are addressing.
so I take it what you're doing is improving the standards that have been historically utilized, perhaps not going completely to a point where it may not be cost beneficial to go to that extra level of improvement.
That is correct. And we're also targeting specific areas. So that
Right.
wouldn't just be changing distribution standards to go all grade B construction everywhere. It's, hey, where do we actually have high wind loading? So we're looking at those coastal areas. Again, looking at our data where we've had structural damage from high winds in previous storms, and then looking for opportunities that to make those changes to the.
And I take in prioritizing those areas, do you look at service interruptions or problems that have occurred in the past? Is it that type of historical
It is
data?
the number of customers that are served, and
I see.
once we've made those improvements, what would the benefits be, and leveraging those that are the highest benefits in those areas.
Thank you.
All right, at this point, we're going to take a short break for the court reporter. We will have a recess and we will come back on the record at 4 o'clock. Thank you. please. All right, Mr. Brown, y'all may continue.
All right, Mr. Malley.
All right, good afternoon. I'm Dan Malley. I'll be speaking to our transmission projects. We are going to start off with an overview of the project areas, and then I'll be drilling down into some specific project locations. One thing I'll mention off the bat is you will notice some similarities between the distribution programs that Mr. Guyton spoke of and the transmission projects that I will speak of. Some of the terminology is a little bit different, whereas distribution is arranged in terms of programs and projects. The transmission portfolio is arranged in terms of 7 unique transmission projects and then resultant project locations where we are actually implementing the work. I will talk through some of the details there. The commonality really between the two is we are both bundling work in common geographic areas to most effectively and efficiently plan and design and schedule and implement the ultimate work. I'll start off by describing some of the characteristics that will be enabled by the transmission project areas. System intelligence, the first category here. We're really improving grid awareness for our grid operators and engineers through the installation of intelligent field devices that get more information back to our operators so they can make smart decisions about manipulating the grid, restoring customers. Our hardening and resiliency project, similar to what you heard for the distribution system, we are targeting a stronger and more resilient grid through both the prevention of faults and the mitigation of faults when they do occur. Our transformer and breaker upgrade project, this is really about preventing the impacts of future failures. We're targeting assets that are at end of life, and we are proactively replacing those prior to failure, prior to the point that they cause either a direct outage or a voltage sag on the grid that can impact our sensitive industrial customers or other problems. And then finally, capacity and customer planning. This is about meeting customer and capacity demands and obligations. The transmission under the transmission system, we're obligated to meet our NERC reliability standards. We're also obligated to meet our new customer connections for commercial, industrial customers, and of course, coordinating with our distribution department for retail customer needs. I'll introduce here a view of the portfolio view of the transmission projects. What you can see on the left side is sort of the investment view. This is the Duke Energy Progress system level investment across the various project areas. And I'll talk a little bit more into the various improvement categories here on this slide. I mentioned intelligent equipment upgrades under our system intelligent project. This is installing digital relays that have much more capability than the legacy electromechanical devices, primarily made up of cams and levers. Again, this is getting more information back to our grid operators. Hardening and resiliency is broken down into several categories. Transmission line hardening and resiliency. This is really upgrading structures. You think about replacing wooden structures with steel structures for our H-frame. We'll see some pictures of that. And also replacing transmission towers that are at the end of life or subject to failures due to certain degradation mechanisms. And when we upgrade these towers and structures, we're rebuilding them to the latest standards capable of withstanding more extreme weather events. This project area is particularly beneficial during those storm events and extreme weather events. Vegetation management, very similar to the customer delivery project. The hazard tree removals we are targeting are outside of the right-of-way. We identify threats. We remove the trees that could result in threats and impacts to the transmission system. The transformer and breaker upgrade project area, both of these projects are about targeting assets that are at the end of life, proactively replacing those assets, and at the same time, we're upgrading the capability of those assets. So when we replace a circuit breaker or we replace a transformer, we are installing, in parallel to this, upgraded communication devices, protection and control relays, again, to be able to better control that equipment, restore that equipment following an outage condition, and get more information such as system voltages and currents and power back to our grid operators and our grid engineers responsible for end-of-life planning. Capacity and customer planning, this is our largest category of work here. You can see on the bottom of the stacked bar chart. This is expanding capacity for customers as load is added to the system, as resource population centers change and move around the state. We have to plan that into our substation and transmission circuit projects. We're also informing these projects through our ISOP process that you heard of earlier. So as we look at a capacity need, we are screening that through our ISOP process to look, is there a non-traditional solution or a non-wires alternative to a traditional transformer upgrade or a circuit rebuild? And that's allowing us really to look at the best benefit to cost ratio for the given solution and move forward with implementing it. This category of work also includes our transmission expansion projects. These are sometimes referred to as the red zone expansion projects. And what these projects are targeting is looking at the areas of the Duke Energy Progress system that have the maximum solar viability from ability to connect solar generation resources. And we're overlaying those areas with areas of the grid that are constrained. And I use the term maxed out or near maxed out. They are very limited to be able to add additional renewable energy resources. And we are targeting upgrading those circuits and in some case substation equipment to accommodate additional renewable energy resources. And for Duke Energy, this is a very important part of our clean energy transition to be able to deliver to our customers a cleaner energy future. The secondary benefit of these projects is we're delivering reliability benefits. We're replacing aged conductor. We're replacing wooden structures with steel structures designed to the latest standards. And we're hardening those systems as we rebuild the circuits. The last thing on this slide I'll mention is the cost by the overall project as well as by the project location is included in the transmission details exhibit. And I will note that the project location details and costs are as of early June timeframe. And these projects continue to be refined as we move them through our development and estimating process under our project management process, particularly those projects in the outer years of the 3-year multi-year rate plan. So as those advance in maturity between June and when we ultimately file the rate case, we will expect to see some changes in both in service dates and costs associated with these projects. I'd like to talk a little bit about how we've built the transmission multi-year rate plan portfolio and how we've selected the project locations that are included. What you see in the middle of this slide are two different organizations. Our system planning organization, again, similar to Mr. Guyton talking about distribution planning engineers, transmission planning engineers are looking at capacity needs for the system. They're working very closely with our distribution planners and our generation planners as well. Our system planning engineers are also responsible for our NERC compliance obligations, ensuring that we meet the obligations of the North American Electric Reliability Council, and that as we model the transmission system and model certain failure scenarios, we will not overload the system. We will not result in catastrophic impacts, cascading impacts, brownouts. So those planning engineers are responsible for that part of the portfolio. The asset management engineers and subject matter experts are really about end-of-life planning. So I mentioned predicting where we're going to have future failures and preventing those failures. Technology upgrades to facilitate a smarter grid that is more capable of providing us information on where failures will occur, where problems on the grid are occurring. So we take various different inputs from field inspections, from asset health trending, technician and lineman input, industry and industry data, and we take that information. We target the specific location that needs work, and we initiate and we score that project in a variety of areas. And what you can see around the outside of the circle here are the different areas that we're looking at from a benefit to cost perspective. We use a third-party software that is specifically designed with various value models to build a benefit. And in terms of each specific project location, we score that project to in the various value models to determine that benefit. So we're looking at financial risk, security and safety, compliance with our regulations, environmental and property impacts, grid capacity due to growth and changing demands, and then of course reliability and integrity. Pause for a moment. Reliability is really the largest area from a benefit perspective. Similar to the customer delivery organization and the distribution grid, we're using the ICE calculator to determine the cost of an avoided outage. We're essentially looking at if we can avoid this outage, how do we monetize that cost, and how do we use that as the benefit that would be achieved through the project in that specific location. And again, similar to Mr. Guyton, we are using DEP specific information. That ICE calculator is actually embedded in our third-party software that we're using for this prioritization framework. Again, we've worked through the benefit to cost analysis for those locations, and the most beneficial projects are optimized and ultimately built into our multi-year rate plan. The last thing I'll mention is we are evaluating the specific different mix of customer classes when we look at a benefit. So we're using 3 different classes: residential, small C&I, and then large commercial and industrial as well to factor into our benefits. I'm going to start diving into our specific project areas, and I will talk mainly about the description of the project, and then I'll get into the benefits of these projects, and we'll look at one specific project location in each of the 7 areas and talk about what that looks like. So what does system intelligence mean? Quite simply, as I mentioned earlier, it's our ability to obtain more useful data about the grid and about our assets so that we can make smart decisions in the best interest of the reliability of our customers. Digital relays, you can see in the bottom right picture, these blue boxes on the screen are digital relays. They're small computers that are installed in place of traditional electromechanical devices. What is a relay? It's simply a device that senses a problem on the transmission grid, generally a fault condition, and it sends a signal to a circuit breaker to open the breaker and isolate the fault. We're very interested in keeping faults isolated to the smallest possible section of the grid, and that minimizes the impacts on customers when we can effectively do that. These digital relays are not only more reliable in sending those signals to circuit breakers and very quickly, in a matter of fractions of a second, isolating faults, but they also provide supplemental information to our operators and to our engineers. The historical means of actually finding a fault on a transmission line, you could think of a long transmission line, maybe 30 miles or more. When we have a fault and we have no intelligent devices telling us where that fault occurs, our energy control center only knows that the breakers on each end of this line opened. Somewhere in the middle of this 30 miles, we have a problem. We have to dispatch linemen and start driving down right-of-ways. In some cases, it's very difficult to access these right-of-ways. They're not generally along roadways. With intelligent devices, we have a better idea, and in some cases, a very specific location down to the structure number on where that fault occurred. We can use technology and algorithms to take that fault current that comes into our system, plug that into an algorithm, as I mentioned, and determine the distance to fault. We can then dispatch the lineman directly to that location. They can assess the problem. They can determine if there's a switching solution, which I'll talk a little bit more about in another project area. Or they can determine if there's a repair that they can immediately make. Perhaps it's cutting a tree off a line. Perhaps it's replacing an insulator that was damaged by lightning. This is the real benefit of our digital relay upgrade program project area. Remote asset monitoring is the second item I'll mention here, both remote asset monitoring and substation monitoring. Most folks are familiar with traditional SCADA, which is getting information from substations back to the control center, being able to control that equipment. When we talk about asset monitoring, that takes SCADA down to the level of a specific asset. In this case, transformers. Transformers are a very important asset on the transmission grid. They're transforming voltage from various different levels within transmission voltages and down to distribution levels to distribute it out to customers on the grid. When these transformers can tell us, hey, I have a problem. I am sick. I need attention. That's a huge benefit. I'll share an analogy here. I recently received an email, and taking a look at it, it said, your printer is low on ink. Very simple technology. Said, your printer's low on ink. You have X amount of pages left to print before this asset fails. That's the type of technology that surprisingly in many places of our transmission grid, we have not yet implemented because the technology is relatively new. This condition-based monitoring technology where we can have an inline gas meter analyzing potential fault gases that are accumulating in our critical power transformers, sending that information to our engineers and subject matter experts so they can make these decisions on essentially how long do I have before this transformer fails or before I need to take it out of service to proactively inspect it or do some additional maintenance. So that's really our asset monitoring program. Remote switches, I'll talk about more on our next slide here. I'm going to go back to the example of when a line locks out. So we have a fault on the transmission system and two breakers at either end open. The transmission system is constructed with various line switches. These are large switches at the 230 kV and 115 kV levels generally. And these switches do allow some operational flexibility to be able to further segment faults and isolate those faults down to smaller areas so then we can restore customer retail stations. We heard discussion about retail stations earlier, which serve the majority of our customers. Traditionally, these switches are manually operated. So again, that lineman, once the fault is identified, once the location is identified, they will then have to drive to a switch, which could be multiple miles, tens of miles away from where they're at. Open the switch using a crank handle, notify the control center that now they can restore load using breakers at the substation, and the control center can make that action. We are deploying more remote operated switches, both in new locations and upgrading manual switches with these remote operated switches. This gives the capability for grid operators to be able to make those switching manipulations remotely from the control center. When we combine that technology with digital relays that give the location of the faults, we go from a matter of hours to resolve a transmission outage to minutes. So there is still some manual action from the control center required, but it can be done in a matter of minutes. And I would call this program somewhat akin to the self-optimizing grid program on the distribution side. It's really a significant way to mitigate the impacts of a fault or an outage occurring on the transmission system. This specific project location is the Delco Whiteville remote control line switch installation. This transmission circuit's in the coastal plain area of North Carolina. It's susceptible to flooding. It's in low-lying areas. You can see a kind of a swampy area in the bottom right picture on this right-of-way. It's very difficult to access. When we have a lightning strike or a tree that comes down onto a line or some other, could be a component failure itself, a structure failure perhaps during a weather event or a hurricane event, it's very difficult to access and restore and make that repair. By having these remote operated switches, we can really tighten up the area of the faulted segment of line, restore more customer load in a faster scenario. So this specific project improves the reliability for more than 11,000 customers directly served off this transmission line. And that's from 4 separate substations. The line hardening and resiliency project will be the next one I'll discuss. Several different areas where we're targeting improvements in this area. First one is our cathodic protection project. Now you'll see down in the bottom left a picture of a failed transmission tower. This tower actually came down during a hurricane event, and post-mortem inspection revealed that the tower legs were corroded. Many of our transmission towers are direct embedded into the ground, which means their support structure may be embedded underground, so they're subject to groundwater and soil corrosion environments. When we install a cathodic protection system, which is a series of protective anodes actually attached to those tower legs, we are protecting and arresting and mitigating the corrosion on these metal towers. And that greatly improves the structural integrity of these towers, particularly again during extreme weather events where we have high wind scenarios, where we have scenarios that are susceptible to cause damage to a transmission tower. The targeted line strengthening for extreme weather scope, you can see a picture in the middle here. This is a typical H-frame design transmission structure. This is very common in our territory on the 230 kV and 115 kV systems. What we are doing is replacing vulnerable and aged wood poles and upgrading them with steel poles. When we replace a wood pole with a steel pole, we're designing that to the very latest standards. We heard about the NESC standards earlier. In a coastal area, for example, a new pole that's installed is designed up to 140-mile-an-hour wind scenarios. So that's a great improvement over the traditional design that in the traditional standards that were in effect when these poles were installed 50, 60, 70 years ago. So again, we're targeting specific poles that we've identified as degraded. We're upgrading them to steel. And in most cases, we've greatly reduced the chance of that pole failing during a extreme weather event or other scenario. Transmission towers, very similar. We're targeting specific types of transmission towers that are susceptible to failure. In these cases, the degradation is not just at the ground level, but it's up higher parts of the tower, and we can't arrest the corrosion or the degradation through a cathodic protection. So we're targeting replacement. I'll talk about a specific example of that on the next slide. The last one I'll mention is the animal mitigation project scope. And this is a specific project targeted at our 500 kV system. One thing that occurs on the 500 kV system is buzzards love to roost on 500 kV towers. You can see these as you're driving under systems down highways and certain areas past our largest transmission towers. Buzzards result in contamination directly underneath where they roost, and that results in flashover events. And these flashover events are very significant on the 500 kV system, particularly impacting our industrial customers. So when we have sensitive manufacturing companies connected to our transmission grid, the faults in the voltage sags that happen on the 500 system, they transfer down into the 230 kV, the 115 kV, and even down in some cases to the distribution level voltage. By preventing those faults from occurring through animal mitigation cover-ups, we are eliminating that voltage sag from that structure that the project is implemented on. You can see the benefits and the CBA numbers here. I'm going to jump right into discussing a little bit more about this specific project location. This is the Mayo Person 500 kV targeted line strengthening project. And what you see is the picture on the left, you see a bolted joint. These transmission towers have many hundreds of bolted joints. This specific line is designed of a material called weathering steel. And it's a steel material that has a corrosion patina on it. It's a brown in color. And ideally what that does is arrest and prevents any more severe corrosion from occurring. What has begun to happen on these towers, though, and this is a common issue in the industry with this design of transmission tower, is these joints, these bolted joints are actually expanding due to corrosion, and they're creating tensile stresses on these bolted joints that will eventually lead to bolt failure and weakening of the tower. The 500 kV system is really the super highway, right, of the transmission system. You heard Mr. Guyton talk about the transmission system as really the highway system. And if we think about the 230 and 115 system as our state routes, our 500 kV system is really those interstates, right? It's your I-40s and your I-95s. It's very important to move large amounts of power around the system. Our customers are typically not directly connected to this system, but it's very critical, particularly in peak winter and summer seasons. This particular line supports about 500 megawatts of network flow, which is enough power for 300,000 homes. So a very significant amount of power flow through these lines. And it is our mission to prevent the failure and the resultant emergent tower replacement costs and potential power flow impacts that could happen to our transmission grid if this was to occur, depending on the type of year where this would occur. The last thing I'll mention on this Mayo Person project is the solution to address the corrosion concern with this type of tower. We looked at multiple different solutions, multiple different types of repairs and replacement options, and replacing the tower with a non-susceptible material that is not subject to this corrosion phenomenon is selected as the best solution from a benefit to cost standpoint, and ultimately the standpoint to be able to reliably serve our customers in all of our weather conditions. Next slide is the substation hardening and resiliency project. Several different project areas I'll go through here. Substation rebuilds is the first one. Substation rebuilds are all about replacing degraded wooden structures within our substations. Many of our substations that transmit power from the 230 or 115 kV system down to distribution level voltages, 24 kV, 13 kV in some places. Those are using wooden horizontal and vertical members. So similar to the wooden transmission tower program, our substation rebuild program is eliminating these wood structures. You can think about these wood structures as really the skeletal system of the substation. They're supporting and holding up the vital organs, right? The transformers, the breakers, the instrumentation that's really critical for delivering the power to our customers. When the skeletal system starts to fail, the supported assets start to fail. And what we're seeing is that these wooden structures are splintering, they're warping, they're causing equipment to come out of alignment. And we're replacing those with steel structures. And at the same time, we're upgrading our targeted breakers, transformers, and system intelligence scope work that overlaps with our other project areas. The substation flood mitigation scope, pretty straightforward. We are mitigating the impacts of floods. We are either relocating substations out of flood-prone areas or elevating equipment, or in some locations, building a flood wall. Animal mitigation. The animal mitigation scope is really installing animal mitigation fences around our substations. Animals are a very significant contributor to transmission outages. When an animal contacts equipment inside a transmission station, the design of the equipment is typically to lock out. So the breaker opens, right? This prevents more significant damage to equipment and collateral damage. So when animals contact lines or circuits, that's not always the case. Mr. Guyton talked about momentary impacts. When animals impact substations, it's a sustained outage that often impacts customers. By putting in specialty fences, we're preventing snakes and squirrels and raccoons from getting into our stations, greatly reducing the chance of an animal causing an outage. Physical security, very similar, except instead of animals, we're keeping people out of substations. So whether it is intentional or non-intentional, our most critical substations, we're installing high security fences, we're installing intrusion detection equipment, and other related security equipment to make sure that we know the status of, and again, keeping people out from causing intentional or unintentional damage or harm to critical transmission substations. A specific example I'll mention for substation hardening and resiliency is our Rayford South 115 kV substation rebuild. You can see an example on the lower right of what these wooden structures look like that support equipment. And on the left is the transformer at Rayford South that we're targeting the upgrade on. And again, I'll talk more about transformer upgrades and the drivers there in just a moment. But this is rebuilding this substation, replacing the equipment that is in need, that is at end of life and is at risk of failure, to prevent those future impacts to our customers. And again, eliminating those wooden structures, upgrading everything to steel structures designed to the latest standards. This is a smaller station. It serves approximately 1,000 retail customers. Still an important station for our retail customers in the Rayford, North Carolina area. Vegetation management. Our vegetation management project area is very similar to the distribution project you heard of earlier. We're really targeting hazard tree removals outside of our right-of-way. What you can see in the image on the left here is a scan that was taken from an aerial patrol. All transmission circuits are patrolled using aerial flights on a periodic basis. We're actually scanning our transmission circuits, and we're building a hazard tree risk model to specifically target area or identify areas that we have risk with a potential tree fall in. So the red polygon areas you can see in the picture here, these are actually called threat areas. And this is our tree canopy risk model. Once we have our threat areas built from the scanning, we have our subject matter experts review the right-of-ways and determine if further action is needed. In most cases, if further action is needed, we go remove the tree. The tree may be particularly tall or particularly wide, and the scanning technology actually determines if this tree fails. Based on the location of the center line of the conductor and where the tree is, it will impact the transmission line or not. So we're specifically targeting these trees that will impact a transmission line upon failure and upon falling into the right-of-way from outside the right-of-way. The work executed, again, under this project is really looking at not just trees that are unhealthy or that are already leaning, but it is looking at any tree that could potentially cause a problem on that transmission circuit. A specific location that I'll mention here for this project area is our Harris plant to Siler City 230 kV. Before I get into that, I will mention another similarity to Mr. Guyton's discussion. The hazard tree removal or vegetation management project does not have a quantitative cost-benefit analysis. It's a qualitative analysis, and for the same reasoning, we see this as an obligation to serve our customers. This is a necessary program area that we've executed for some time. The Harris Plant Siler City 230 kV line south of Raleigh here. This is a 33-mile line connecting the Harris Nuclear Plant, approximately 1,000 megawatt generating station, to 3 different substations and 4 different transformer banks. This serves approximately 20,000 customers. This is a 100-foot right-of-way. Our scanning, which is using a LiDAR technology, it's a type of scan. We are identifying threats up to 30 feet outside of that right-of-way, and then we're proactively targeting removal of those trees that have been deemed to be threats and fallen risks for that transmission line. For transmission-specific outages, about 25% of customer minutes interrupted are from trees from outside the right-of-way. So 1/4 of all customer outages that emanate from the transmission system are coming from trees outside of the right-of-way. So it's a very significant project for us for customer reliability. I'll move next into our circuit breaker upgrade project. This upgrade project is targeting assets that are at the end of life. Particularly, we're targeting oil circuit breakers. Oil-filled circuit breakers are a legacy technology. It is an oil-filled tank. That oil actually arrests the fault and the arc gases and extinguishes the arc when a circuit breaker opens or closes. It's an outdated technology, and these breakers are prone to failure. Our strategy here is identify assets that are beyond the end of useful life, that have a expectation for failure based on make, model trending that we have based on the number of operations and the number of faults. That's data we gather. Essentially, the more a breaker operates, the more wear it is getting. We also are targeting locations based on the number of customers served, the configuration. Is it networked? In other words, is there redundancy, or is it a radial system? There is no redundancy built in. So we're taking all these inputs, we're targeting the locations, and then we're replacing that oil circuit breaker with an upgraded technology. We're using vacuum circuit breakers. It's a vacuum chamber that extinguishes or prevents an arc from occurring for distribution level voltages. So that would be transmission assets in a transmission substation, less than 44 kV. And then for the higher voltage assets, we're using pressurized gas breakers, which is the state-of-the-art modern standard for fault interruption at the transmission level. And again, as we upgrade those assets, we're installing upgraded protection and control relays, digital relays that can get us that additional information for remote monitoring and control of the grid. One important factor with circuit breaker is, and I alluded to this earlier, if a circuit breaker does not operate reliably to isolate a fault, the section of the transmission grid that isolates grows, right? The backup breakers need to operate. So this could be at remote substations, further out on transmission lines, at adjacent transmission stations, and therefore more customers are interrupted. So getting a circuit breaker, ensuring a circuit breaker reliably operates the fault when given a signal to open is very important to minimize the impacts on our customers. Every time a circuit breaker fails, when I'll say two things. When a fault occurs, and particularly when a circuit breaker fails to open, in addition to that direct failure for the customer served from that line, we're also getting a voltage sag on the system. So this is the same for a transformer failure as well. These failures do result in significant voltage sags that impact our sensitive industrial customers and manufacturing customers. So it's our goal to prevent those impacts and proactively address these assets. This specific project location, the Millburnie 230 kV substation, supports the greater Raleigh area. This is east of Raleigh. And we are targeting the replacement of 5 115 kV circuit breakers. You can see a picture on the lower right of what these oil circuit breakers look like. This specific station, I mentioned, is very critical. So 5 different lines come into this station. Those lines go out to serve 77,000 customers. In this specific station, we actually had a recent outage event where one of the breakers did fail to operate in the required clearing time, and breakers further out opened. We directly impacted 17,000 customers on that one outage event. So a single fault on the transmission system and 17,000 customers impacted. So that type of event is exactly what we're looking to avoid and eliminate, or greatly reduce the impacts of during while executing this project. Transformer upgrades, again, some parallels to breakers. I mentioned earlier, our transformers transform voltage from transmission levels to other transmission levels. So 500 kV to 230, 230 to 115. That's for connecting out to the various levels of the transmission system for bulk power flow. And then they also transmit or transform voltage from the 230 kV system, the 115 kV system, down to the 24 kV system commonly in the DEP area. So these are critical assets for serving our customers. What we're doing is, again, we're targeting specific transformers that are at end of life. We're using field inspections, visual inspections, electrical testing. We're using make, model information, trending information, vendor and industry data to select what assets are prioritized for replacement. We're scoring those projects, again, using the model that I talked about earlier on, based on that specific location, the number of customers served, the voltage level, et cetera. This project also includes regulators. Regulators are substation regulators specifically are very similar to transformers. One moment. Whereas transformers transform voltage over large areas, regulators control voltage over a very tight band, so plus or minus 1 volt in some cases. And we are obligated to maintain this voltage out on our systems. And you heard a little bit about voltage regulation earlier from Mr. Guyton. A regulator in a transmission substation controls the voltage for all the circuits leaving that station. And we'll look at an example of that on the next slide. One of the key things this project eliminates is a vulnerable arc in oil design for load tap changers. As we see more and more renewable energy resources, and particularly variable energy resources, connect to the grid, this arc in oil technology is a specific vulnerability. But essentially, it's an oil tank where, again, similar to a breaker, as a voltage regulator or a transformer controls voltage, there's an oil tank where this arcing occurs. Gases can accumulate in that oil tank over time and lead to catastrophic failure. When a transformer or a regulator fails catastrophically, there's often release of oil. There is often collateral damage due to the size of this equipment and the amount of energy that's stored in there and the amount of oil that's stored in there. So in addition to just that, asset replacement costs that come in a substation can be very significant from a cost standpoint and also from a time standpoint for recovering from that outage event. So again, these are reasons why we want to proactively address these assets that are at end of life, replace them prior to failure, prior to the customer being impacted, and prior to the grid being impacted by that failure. New designs use a vacuum load tap changer that eliminates this vulnerable technology, particularly susceptible to when we have variable energy resources and we have a lot of voltage regulations as we see cloud cover changes. The specific example or project location I'll speak to for our transformer upgrade project is the Wilmington Ogden 230 kV three-phase regulator replacement. This is in the Wilmington, North Carolina area. We are replacing a three-phase station regulator. This one regulator provides voltage control for 4 different distribution circuits leaving that station. Those circuits serve over 8,500 customers. The last thing I'll mention here is three-phase regulators are the top outage cause category for substation equipment failures in DEP for, again, outages emanating from the transmission system. When we look at substation equipment, we've had over 11 million customer minutes interrupted in the last 5 years. So it's very important for us to target these assets, upgrade these assets with or with designs that are less vulnerable to these failures. I'm going to move on to the last project area, which is our capacity and customer planning project area. This type of work is very critical to meet the capacity needs of our customers. I mentioned earlier our interrelationships and working between our customer delivery planners, our generation planners, and our transmission planners, making sure we can project the needs for growing and shifting customer demands in our territory. In addition to this, we have an obligation to meet our NERC compliance requirements. And this includes modeling the transmission system under certain failure scenarios. Because the transmission system can impact so many customers upon a single failure, we have compliance obligations to plan for a single failure scenario and plan for different scenarios that may impact the grid. So if we lose certain equipment, what's the resultant impact? Will it result in overloads? Will it result in cascading outages? Impacts that go much beyond one substation to larger areas of the grid. So this project area is all about mitigating those impacts and planning for those future potential consequences to the grid. I mentioned earlier, these capacity projects are informed through the ISOP process. So we are screening capacity upgrades for non-wires alternatives, such as battery storage. And we are moving forward with the best option from a cost-benefit perspective approach. I'll talk again about our transmission expansion plan, aka our red zone projects, and go into a little bit more detail here. We have 11 projects that are targeting capacity upgrades in our territory. Again, these red zones are areas where we have maximum solar viability and we have minimum capacity. We feel it's truly important to transform the grid to the clean energy future, and upgrading these lines is really a key part of that transformation for us. The many interconnection studies over many years have identified the need to upgrade these circuits and have proven the need. We are also processing these projects through the North Carolina Transmission Planning Committee and the Transmission Advisory Group specifically to obtain stakeholder input. The Transmission Planning Committee Oversight Steering Committee will ultimately have to approve these projects, and this is all in line with FERC requirements for transmission additions. These projects are an important part, not just from the energy perspective, but also an important part of our plan from a reliability perspective. We're delivering significant reliability benefits, and we're also evaluating these projects under a traditional benefit to cost reliability model as we do our other projects. We are looking at the conductor replacement, the structure replacement, and the mitigating impacts of, preventing failures due to upgrading that equipment. We do understand additional discussion on these projects is ongoing with carbon plan proceedings. One specific project location I'd like to discuss is the Craggy Anchor capacity project. And this project, you can see on the picture on the right side, the north and south parts of this is the general Asheville area. You can see the yellow line. That's an existing 230 kV transmission circuit. Conspicuously in the middle, there is no 230 kV circuit between the Craggy and the Anchor substation. So we're missing this corridor in the central Asheville area here, or to the west side, where we are limited at how much power we can transmit between the different parts of the system. And our planning models have actually identified a potential load shed outage scenario by the winter of 2025, based on limited ability to move bulk amounts of power between the system. So we're building a 230 volt connector line between these 2 points. And we're doing that in a least impact way as possible. We're using an existing 115 kV right of way that spans between these 2 stations. You can see an artist rendering in the lower left hand side of the picture where we're actually going to be putting the existing 115 kV circuit rebuilt on one side of the structures, and the new 230 kV line on the other side of the structures. So I mentioned the benefit. Directly, this project serves approximately 30,000 existing customers from this line, and in the greater Asheville area, a much larger number of customers for general voltage stability and grid stability in the greater area. Okay, and the last slide will be our closing remarks, Justin.
Yeah, if you want to click the last slide. I just want to say, we've certainly provided a lot of information today and in our pre-filing materials that we did. We believe the projects today for both transmission and distribution complement each other in supporting the clean energy transition in North Carolina, really to build a grid that can accommodate two-way power flow, that has increased automation, overall situational awareness for the grid, and really postures us overall for increased reliability and resiliency overall for the system. Certainly postures us for a safe expansion of renewable generation and distributed energy resources at the edge of the grid, along with providing equitable benefits for customers across the entire system, done in an affordable way. Thank you for your time today.
All right, thank you all. Let me check and see if there are questions from the commissioners. Commissioner Clodfelter.
This is a general question that speaks to both components. If you're able to do so, and secondly, if you're willing to do so, I understand both conditions have to be met. Can you forecast whether any portions of these proposed projects will be associated with a performance incentive metric in the upcoming rate case? Or are they going to be tied to a performance metric?
So I do believe that performance incentive metrics are a required component of an MYRP filing.
They are, but you only have to propose one out of a basket of several you could propose, and I'm just trying to find out whether this one might be one of the ones you're going to propose.
When you say this one?
Associated with your distribution and transmission projects, are you going to propose any performance incentive metrics to measure your success or failure?
I do know that there will be at least one, but I don't know if they're specifically tied to these.
Don't know if it's going to be associated with these projects. That's all right. As I say, you might not know, but even if you know, you might not be willing to say today, but I thought I'd ask the question, see. All right. Thank you.
All right, additional questions for DEP? I see Commissioner Duffley, your hand is up.
Yes, thank you. So going to slide 40, you were talking about new delivery points for customers. And so my question is, which type of customers? Are you speaking of retail customers or wholesale customers? And then if you're speaking of retail customers, are you speaking of residential, commercial, or industrial?
Sure. Thank you for the question. Generally, industrial customers would be the new customers that the transmission portfolio would sponsor a project for, that would be new industrial customers directly connected to the transmission system. The retail projects would typically come through sponsorship of the customer delivery distribution arm.
Okay, thank you for that clarification. And then on page 42, you were discussing the reduction of faults. I just would like a sense of how many faults the transmission system sees per year.
Sure. It can vary widely, particularly during storm scenarios. If we look at sustained fault, sustained number of outages, year to year, it can vary from 50 to 100 outages. That's not uncommon. The average over the past 5 years, it's approximately in the 70 range for sustained faults. Momentaries, significantly higher than that. The transmission system is built with reclosing capability on the circuits. So many hundreds of faults obviously occurring on the transmission system when you look at momentaries on an annual basis.
Okay, thank you for that. I don't have any further questions.
Right, I would like to follow up on the response there. So a momentary fault, does that result in a disruption of service to customers, or can you help me understand what that means in practical terms?
Yes, good clarifying question. A momentary fault is a fault that interrupts customers that lasts for, on the transmission system, 1 minute or less. So a fault that occurs for 59 seconds would be a momentary, 1 minute or more would be a sustained outage. So it's certainly an impact that customers would notice, particularly for those commercial and industrial customers, can be consequential even at the momentary level.
Okay, thank you. All right, Commissioner Klopfelter.
I'm going to be asking a question. You may not have it there in front of you, but the question is really comes from Exhibit TC-9C. And I really just want to understand what that exhibit is telling me. So these are the capacity and customer planning projects. And there is a table showing the costs, the operational benefits, the customer benefits, and the combined costs and benefits. And I followed the chart through the cumulative net benefit turns positive starting in 2035 and in later years out. So it's a upfront investment that you recover over an extended period of time. What I really want to understand is the line under customer benefits that's titled residential/commercial/et-cetera customers. So, I mean, you've got a line above that, which is the customer outage benefits. So I assume that that second line, residential/commercial/customers, really doesn't include a lot of outage benefits or traditional reliability benefits. It's including something else there. And what is that? Is that load growth? If it's not load growth, a lot of these projects, as you've already said, are red zone projects that are increased system capacity to absorb additional renewables. And so how does that translate into the number that's shown on that line of customer benefits? Are those societal benefits?
So I am looking at that exhibit, and what I'm seeing here is actually the avoided customer sustained outage benefits dash residential, commercial, et cetera customers is all one row.
Oh,
And then
that's
total
not two
customers is
rows. That's not two rows. It's a single row.
That is correct. That is correct.
Caught me. You caught me on that. So that number then does include the value of outages avoided and the cost of outages avoided.
Yes, sir, that's correct. That is using the ICE model. The societal benefits in terms of avoided outage, in terms of avoided outage costs.
Sure. But in terms of, for example, the projects that are on the list on page 5 there, a lot of which are the red zone projects. I've begun to recognize them by now, individual projects. To the extent those are enabling retirement of carbon resources and substitution of renewable resources, is that substitution being valued in your cost benefit analysis? And if so, how's it being valued?
At this point, those benefits are not being valued quantitatively.
So that, then on this TC 9-9C, that line that we just looked at, which you've now explained to me is a single line, not two lines, does not include the benefits from the enabled conversion from fossil to carbon-free resources.
That is correct. Yeah, of course.
Thank
there
you,
is
sir.
Difficulty in quantifying that. It's certainly something we are interested in the future.
We're all interested in it. I just wanted to figure out if you'd found a way to quantify it and put it on this page. That's what I was trying to find out. Thank you.
While you're looking at TC9C, page 5 of 5 of that exhibit, can you just point me to the 11 projects that are in the red zone? And I'm wondering if they're located on that page 5 of 5, and if not, where would I find them?
Sure, you can, they are listed, let me just get to that page. We don't have them uniquely called out as sub projects.
Right.
Within here. Now, they are also listed. I'm going to go to a different exhibit because I have them more easily marked up. And the technical conference MYRP project details transmission exhibit. And I don't have the number right here. But they are listed in there. I can go through the titles of the locations if you'd like them, or we can provide that in follow-up.
Just provide it in follow-up. That would be helpful.
Okay, thank you.
And just to make sure, because I think I missed you, that the exhibit you are just referencing, is it?
Make sure.
7?
Yes, that's correct.
Okay, all right.
TC7, yes.
Okay, thank you. While I have the mic, I'm going to ask you one more question about the ICE calculator. I've heard you reference it now several times, and we talked about it during the discussion on the distribution programs. And you mentioned that you all have a third-party model that you all are using that incorporates the ICE calculator. So is the ICE calculator model being used the same way for the transmission side as it is for the distribution side? Okay.
It is very similar. I will say we are using DEP-specific information fed into that. SAIDI, safety are variables, and retail customer class mix, so residential, small C&I, large C&I. It is not exactly the same. So we have that calculator and tables embedded in the software. The software then does that calculation. But from my knowledge and working discussions with my peers and customer delivery, is utilizing the tables very similarly.
Okay. I recognize that benefits associated with investments in the distribution system and benefits associated with investments in the transmission system may be different, but to the extent you're looking at a same or similar benefit, are they being calculated in the same way?
Think about that. Yes. So for an avoided outage, we would calculate the benefit the same way.
Okay. That's thank you. That's helpful to me. That's a good example. Okay. Let's see. Let me see if Commissioner Brown-Bland has a question.
Yes, I do have a question. With regard to your discussion about the right-of-way, the work at the right-of-way, and you gave an example where you were clearing 30 feet outside of the right-of-way. Is that to comply with any standard, like a NERC standard, or does it exceed any required standards?
Yes, thank you for the question. We do have NERC compliance obligations to implement a vegetation management program specifically for our 230 kV system, 200 kV and above. It does not specifically dictate distance outside right away, but we are obligated to have a program and to demonstrate how we are preventing trees from encroaching upon our minimum vegetation clearance distance. So we are going above and beyond those minimum compliance requirements from a reliability perspective.
Based on the work that you've done so far, in examining all of that, is 30 foot kind of expected to be the company's standard, or would we expect to see this change over time? Like, would it expand to 35 or 40 feet out? Or
I am not a vegetation management expert, so I couldn't weigh in on that. I'm not sure the answer there.
okay, thank you.
Okay, we're at 5 o'clock. And I'm going to check in with the court reporter to see how she is doing, if she can continue on. Okay, so since we are close to the end of the presentation from Duke, I'd like to continue. It's my understanding we have one interested party that intends to present. Counsel, I'm looking at you to confirm that.
Yes, Chair Mitchell.
Okay.
SIGFR has a presentation.
Okay, so we will push on then and finish up today, unless someone raises strenuous objection. Okay. All right, well, let's continue on with questions from commissioners. Commissioner Hughes, do you have any questions? And then we'll hear from McKissick and then Kim Wright.
Commissioner Hughes, you're on mute.
All right, Commissioner Hughes, we cannot hear you. All right, let's hear from,
Can you hear me now?
we can hear you now.
Sorry
Go
about
ahead.
that. The three objectives that you laid out at the beginning and then again at the end were grid resiliency, expanded renewables, and DRs. And then you have this equitable access to benefits. We spent a lot of the day talking, it seems to me, talking about the first two, a lot of the modeling that went in, a lot of the technical details. Could you just talk briefly about what process did you go for that third objective? And was there any quantitative modeling for that third objective and kind of making trade-offs and things?
Thank you. I would say that the equitable access to benefits is not really in a quantifiable way. Part of what we are doing when we looked across the distribution and transmission system is making sure that we didn't concentrate necessarily investments or types of investments in one particular area. They're intended to be broad across the DEP service territory so that when new technologies do become available, that all customers on the system can take advantage of those. And specifically too, as Brent and Dan mentioned, by grouping the projects together in a localized area, we believe we're trying to wring the value of the resources that we have on the system, typically labor resources as well as materials, wring the biggest value out of those implementations so that we can have an eye on affordability overall for the customer.
So it's mainly affordability.
Affordability and making sure that the investments aren't necessarily concentrated in one particular area of the system.
Okay.
They're broad in nature.
Thank you.
Well,
All right, Commissioner McKissick.
In the interest of time, this is a pretty quick question. And it kind of follows up on one that Chair Mitchell asked about the 11 projects in the red zone. First, how did you determine which of those to proceed with in this particular proposal that's before, that will be, submitted to us soon? And then secondly, as I recall, and my recollections may be mistaken, there were, I think, 13 projects in the DEP territory in the red zone. Was there consideration given to just knocking them all out, considering the need to meet that capacity, as expeditiously as possible?
Yes, I'll say the number of projects has shifted and shaped some as we continue to sort of most effectively bundle and combine. One project also moved to now it's a need under our transmission additions plan based on capacity changes. So it's moving, it's a little bit fluid. And that may be the difference between the 13 and the 11. These really are the bulk of projects as we see as the priorities now to upgrade. So there may be additional expansion plan projects in the future, but these are the projects that we see over the next 3 years in the time period of the multi-area plan are the critical projects to implement the capacity upgrades on.
Thank you. I guess the thing I would ask as you continue to work on this proposal is perhaps evaluating all of them, and moving forward with all of them, if it can logically be sequentially performed and executed in a way that's, cost effective, that makes sense. Because there's a real need to address these red zone areas as expeditiously as possible.
Thank you.
Thank you.
And to follow up on a couple of questions from Chair Mitchell and Commissioner Clodfelter about the red zone upgrades. On page 55, the benefit cost ratio for the red zone upgrades and the additional part of the program is 1.6, which I think is the lowest ratio of any of the programs. Can you just briefly explain why this is included in your program since it has the lowest ratio of what you're proposing?
Sure, I'll expand on the benefit to cost ratio for our capacitor and customer planning. I recall this project area actually includes the red zone or transmission expansion projects, also includes the compliance of obligated compliance projects for reliability, NERC reliability planning, and new customer connections, specifically industrial customers connecting to the transmission system. Compliance obligations, we do not actually score through a benefit to cost process because they are requirements under federal standards and rules. We do include the costs of those projects. We do not include the benefits. We skip the scoring and they are obligations to implement. So that does drive the benefit to cost ratio overall for this bundled project area lower than some of the other areas. You're welcome.
Just following up there to make sure I'm clear. When you say compliance, you mean compliance with
NERC standards.
With NERC standards. Okay. Okay.
And do you have the ratio for just the benefit cost ratio for the red zone upgrades themselves? Has that been differentiated or separated?
We have not to this point differentiated that.
Thank you.
You're welcome.
Go ahead. Go ahead.
The biggest bang for the buck that you've got on the list here is the Rockingham station uprate for the 500 kV uprate. What's involved in an uprate? How do you, I mean, for less than $1 million, you get $108 million worth of a benefit. You get almost 15% of your total benefit for less than $1 million. What's involved in the station uprate?
In that, can you restate the project, please?
It's the Richmond 500 kV substation uprate.
Okay. Okay. When we look at an uprate solution, there's multiple different things it could be. Obviously, the most expensive are rebuilding a line. In this case, although I'm not specifically familiar with the scope offhand, generally a uprate in a station is replacement of a limiting component from a current carrying equipment perspective. It could be a wave trap, which is a device that is used, current limiting or communication related device that carries current. It could be a smaller type asset within a station. Generally, the more favorable from a benefit to cost perspective or lower cost uprates are substation equipment uprates. Also relay settings. Surprisingly, sometimes we are restricted purely by the settings on protective relays. So by changing those relay settings, sometimes in conjunction with replacing a current transformer or a voltage transformer, we can actually uprate the overall rating of the facility, which would be the station and the connected lines.
Thanks for the education.
You're welcome.
All right, let me check and see if there are any additional questions for the DEP panel before we let them go. All right, well, thank you all very much for your presentation today. We appreciate your being here with us and the explanations you've provided. All right, Mr. Jeffries, if you would, we would like a follow-up filing on the TC7 identifying the projects there.
We've got that noted.
Thank you, sir. All right, you all may step down. Thank you.
Thank you.
All right, Mr. Kress, it's my understanding SIGVR 2 has a witness you all would like to call.
Yes, Chair Mitchell, thank you. And I'll just note at the outset that we only learned moments before this technical conference began that we would be the only party making a presentation. But since our witness is here from Missouri, we are going to go ahead with our presentation, and we appreciate the opportunity to
Okay,
do so.
absolutely.
So with that, I'll turn it over to Bob Stevens with Brubaker and Associates. Thank you.
Good afternoon, Chair. Can you hear me okay?
We can hear you.
Good afternoon, Chair Mitchell and Commissioners. I don't know if there's my presentation. All right. You're all new to me and I'm new to you. I'm Bob Stevens. I'm with the firm Brubaker and Associates here on behalf of SIGFUR, the Carolina Industrial Group for Fair Utility Rates. Those are my qualifications. I won't go through them in the interest of time. I'll just note a couple. I've been in the consulting industry, regulatory consulting and consulting to individual customers on electric rate matters for nearly 25 years. Before that, I worked at the Illinois Commerce Commission, and before that, a utility. I will skip over this page. You know what the megatrends are. We've already covered that. Here I'd like to talk about what are priorities for SIGFUR. We're talking about billions of dollars of spend here, and it's true that there will need to be additional transmission and distribution investments. There's no question about that. But from industrial customers' point of view, it's going to be imperative that we manage the cost of service because right now, competitively priced service in North Carolina at a high level of reliability is helping to drive the industrial economy, which helps drive the overall economy. So we ask that the cost of service be managed and the rate changes be as gradual as are feasible. We encourage DEP to develop capital projects at least cost, considering all options, transmission, production, and distribution, not siloing into one. And we've gotten some indication earlier today that they don't necessarily do that in all cases, but we want to encourage as much coordination there as feasible. And we want to encourage capital budget timing such that rate base doesn't grow in leaps and bounds suddenly. DEP has identified billions of dollars worth of costs here, approximately $3 billion by my count based on the presentation. So we want to make sure that capital spend is conducted in a deliberate and gradual way. And then finally, as part of the multi-year rate plans, there will be tariff rates proposed, and we want to make sure that those are set rationally, that they help encourage conservation among customers by efficient price signals, and that they reflect cost of service. Regarding T&D service quality, it's important that we've heard several options for both supply and demand reliability. We want to make sure that the demand side is exhausted because customers can provide interruptible capacity that can help alleviate some of the stresses on both the transmission and distribution systems. We want to ensure that power quality is maintained and at a least cost. You've heard talk today about voltage stability. For industrial customers, even small or even very momentary changes in voltage can have a detrimental impact. Sag surges, transient changes generally under voltage, that can all affect equipment and production. In fact, voltage sags, even momentary, can shut down industrial plants. They can damage equipment. And when that happens, you have lost production, you have, in some cases, the inability to meet customers' needs. So it's very important to maintain adequate voltage stability as well as frequency. And then similarly, SAIDI and SAIFI and CAIDI are all valid measures, but you heard some discussion by Mr. Maley about what's a momentary outage. Momentary are the ones below 1 minute. For industrial customers, harm can happen within a second. So we should consider another measure, MAIFI, momentary average interruption frequency index, which is a total of the momentary outages in a year divided by the number of customers. Regarding tariff rates and efficient consumption, we want efficient rates, we want fair rates. For the transmission service, costs should be allocated based on coincident demands. For distribution service, at the circuit level, non-coincident demands are typically used. Taking into account customer density and circuit miles is an important factor as well. When prices are efficient, they provide an economic incentive to customers to conserve. For example, if you set your demand rates too high and your energy rates too low, customers will get the wrong signal thinking that their demands don't cause costs on the system to the extent they do, and likewise that their energy costs more. The most efficient functioning of a utility is when the prices reflect costs so that customers can respond accordingly. So I've covered a few things. Here are the key takeaways. The importance of gradualism and avoiding rate shock. We'd like for DEP to be able to show that system reliability benefits exceed the costs of the planned capital, T&D capital spending. Indications so far are that they do, but we haven't dug into the numbers yet, and that will be a part of the filing once made. Delivery voltage should be aligned with embedded costs. If you're taking service at 230 kV, you don't use any distribution assets, and therefore you shouldn't be charged costs of the distribution system, including these distribution improvements. DEP covered the fact that the federal funds are being used. We encourage the commission to make sure those funds are maximized. And then finally, look at things beyond just SAIDI and SAFE for measures of reliability to get to the important momentary interruptions as well. We look forward to digging into DEP's filing once it's made. And with that, if you have any questions, I'll do my best to answer.
All right, thank you, sir. Let me check in with commissioners to see if there are questions for you. Any questions from Commissioners Brown, Bland, Duffy, or Hughes? Okay, I'm not seeing any. Okay, well, thank you very much, sir, for your comments today. You may step down.
Thank you.
All right, and with that, we've come to the end of our day. Thank you again to all the presenters and for sharing this information with us. And with that, we'll be adjourned. Thank you.